The image arrived as a silent triumph of technology and curiosity, a faint, elongated streak set against a tapestry of stars, glimmering at the edge of interstellar darkness. This was the James Webb Space Telescope's first real image of 3I Atlas, only the third known interstellar object ever observed passing through our solar system. For astronomers, it marked a moment of electrifying significance, the fusion of Webb's unmatched precision with the mystery of a visitor from beyond our star's dominion. For decades, the idea of imaging such an object in detail had belonged more to speculation than to reality, yet here it was, the ghostly profile of an emissary from another star system, caught by the golden mirrors of a telescope a million miles from Earth. Before we start, hit the like and subscribe buttons for more updates. The story of 3I Atlas had begun quietly, like many great discoveries, as a dim speck in survey data. When first detected by the ATLAS, Asteroid Terrestrial Impact Last Alert System survey in Hawaii, it seemed to be a fast-moving cometary body. But as astronomers refined its trajectory, it became evident that its path was hyperbolic, meaning it was not bound to the Sun. This was no ordinary comet or asteroid. Like its predecessors, 1I/Oumuamua and 2I/Borisov, 3I Atlas was a messenger from interstellar space, hurtling across our solar neighborhood at tens of kilometers per second, untouched by our sun's gravity except for a brief, graceful deflection. By the time Webb turned its instruments toward it, 3I Atlas had already intrigued scientists with its unusual spectrum. Ground-based telescopes had detected faint signs of volatile material, gases escaping from its surface, suggesting a hybrid nature somewhere between a rocky asteroid and a volatile-rich comet. But these observations were limited by distance and atmospheric distortion. The James Webb Telescope, with its unparalleled infrared sensitivity and freedom from Earth's atmosphere, promised to reveal details never before accessible. When the first image came in, the excitement was almost palpable across the astronomical community. The object was small, but the data it carried was immense. In the Webb image, 3I Atlas appeared as a diffuse nucleus trailing a delicate veil of material, a sign that sublimation was occurring as sunlight warmed its surface. The faint halo hinted at complex chemical processes underway. What captured scientists' attention, however, was not merely the visual aspect, but the subtle differences in light across wavelengths. Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, allowed astronomers to isolate the spectral fingerprints of various compounds. Early analysis indicated the presence of exotic ices, methane, carbon monoxide, and even traces of complex organic molecules, materials that could have formed in the outer reaches of another stellar system billions of years ago. To imagine what this meant required more than scientific curiosity. It required awe. Here was a piece of another world, a fragment perhaps of a shattered planetesimal ejected long ago by a young star's chaotic birth. It had traveled uncountable light years through the interstellar void, crossing regions of cosmic radiation, interstellar dust, and magnetic turbulence, only to pass briefly through our solar system and reflect its story into the mirrors of a human-made instrument. The Webb telescope, with its fine-tuned mirrors and cryogenic sensors, became the cosmic bridge between that alien past and our present understanding. The image, while visually modest, represented a technological and philosophical leap. The precision required to track and capture 3I Atlas bordered on the improbable. Unlike stars or galaxies, which remain fixed relative to one another across years of observation, interstellar visitors move fast and unpredictably. Webb's team had to reprogram its fine guidance system to lock onto a rapidly moving faint target, a challenge that demanded mathematical rigor and operational creativity. When the data arrived intact, it wasn't just a testament to the telescope's design, but to the collaborative spirit of hundreds of engineers, scientists, and mission planners who turned an improbable goal into an image that now defines a new era of planetary science. The implications of seeing 3I Atlas up close stretched across disciplines. Planetary scientists saw in it an opportunity to test theories about how planets form and evolve around other stars. Cosmochemists viewed it as a pristine sample from beyond the solar system, a clue to the diversity of matter that populates the galaxy. Astrobiologists too watched closely, wondering if its organic molecules hinted at prebiotic chemistry common throughout the cosmos. Each discovery layer invited another question, deepening rather than diminishing the mystery. What made the Webb image of 3I Atlas particularly striking was its subtle color gradient in the infrared spectrum. The nucleus emitted slightly more strongly at certain wavelengths associated with hydrocarbons, long chains of carbon and hydrogen molecules. These were the same basic building blocks of life found in meteorites that have fallen to Earth. To detect them in an interstellar visitor was to glimpse a common chemical thread weaving through distant planetary nurseries. The universe, it seemed, might be more chemically uniform than we imagined. A vast theater producing similar ingredients, though perhaps never the same recipes. Beyond chemistry, the Webb data revealed textural clues about the object's surface. Variations in brightness suggested uneven albedo, bright patches of ice interspersed with darker, dust-covered regions. This patchwork pattern told a story of heating, cooling, and cosmic erosion. Over millions of years drifting through the interstellar medium, 3Y Atlas had likely been battered by micrometeoroids and stripped by radiation, leaving behind a crust that partially insulated its interior. As it neared the sun, the latent heat released volatile materials trapped beneath this surface, forming the faint tail Webb captured. This quiet act of sublimation connected 3I Atlas to the ancient lineage of comets, cosmic storytellers that carry within them the memory of star systems long vanished. Astronomers working with Webb's data soon realized that 3Y Atlas was larger than initially thought, perhaps between 1 and 2 kilometers in diameter. Its trajectory was steep, entering the solar system from an angle that suggested it came from the direction of the constellation Cassiopeia. By tracing its path backward, scientists inferred that it might have been ejected from a binary star system, where gravitational interactions are more likely to fling debris into interstellar space. That detail alone opened new doors of speculation about its origin. Could it be a remnant from a planetary disk circling a sun-like star? Or perhaps material from a young, volatile system still in formation? Each hypothesis carried profound implications for understanding the dynamics of planet formation across the galaxy. The sheer act of seeing 3I Atlas through Webb's eyes also underscored how far human observation has evolved. When Oumuamua was first discovered in 2017, humanity could only guess at its nature. It was too distant, too faint, and too fast for any telescope to resolve clearly. Speculations ranged from a comet with no visible coma to exotic theories about artificial origins. Then came 2I/Borisov in 2019, a true comet whose gaseous envelope revealed more traditional properties. Now, with 3Y Atlas, the Webb telescope's image brought unprecedented clarity. It bridged the gap between speculation and direct observation, transforming abstract curiosity into tangible data. In a sense, the image became a mirror reflecting not just the object itself, but our evolving ability to perceive. It represented the culmination of centuries of incremental progress, from Galileo's crude lenses to Webb's segmented gold mirrors operating in cryogenic silence. The photons that left 3I Atlas years ago traveled across the solar system, through the cold vacuum of space, and into an array of sensors designed to detect the faintest whispers of infrared light. The result was more than a picture. It was a moment of communion between two forms of cosmic dust. The alien rock wandering through interstellar space and the stardust-born beings who built a machine to see it. What followed in the days after Webb's capture was a global surge of excitement. Researchers from observatories worldwide began coordinating follow-up studies. Spectroscopic teams analyzed the data, comparing it to models of known cometary compositions. Others simulated the trajectory to understand the object's origin. The Webb image became the reference point for all subsequent observations, serving as the benchmark for how interstellar objects might appear when scrutinized under ideal conditions. For the first time, humanity possessed a clear, data-rich look at matter from beyond the solar system. Not a passing blur, but a discernible, analyzable visitor. The encounter with 3I Atlas also carried a quiet sense of humility. In cosmic terms, the object's visit was fleeting, a brief intersection between two celestial paths that would never cross again. Within months, it would recede into the blackness, returning to the galactic sea. Yet for that short interval, it illuminated the shared material heritage of the universe. the dust in its tail, the ices within its core, the molecules it released into the solar wind. All were part of the same universal chemistry that built Earth and life itself. To witness it was to be reminded that our solar system is not isolated, but part of a continuous exchange of matter and energy across the stars. The Webb Telescope's success in imaging 3Y Atlas also marked a turning point for the study of transient interstellar phenomena. With this achievement, astronomers demonstrated that future interstellar visitors could be captured with comparable precision, provided the response is rapid. It encouraged the development of automated alert systems capable of coordinating telescopes across the globe and in orbit. Webb's role proved that deep space observatories are not limited to studying distant galaxies or the early universe. They can also probe small, fast-moving targets that hold clues to planetary diversity on a galactic scale. What made 3I Atlas unique was its dual nature. It was both a relic and a messenger. Its composition preserved conditions that existed billions of years ago around another star, unaltered except by time and radiation. Every atom within it told a story older than the sun itself. By capturing it in such detail, Webb effectively expanded the boundaries of comparative planetology. Scientists could now analyze an extrasolar object with the same tools used for solar system bodies, allowing direct comparison between local and foreign material. This was not merely a glimpse into another system's debris. It was a data set that could redefine our understanding of planetary formation environments across the galaxy. The telescope's instruments revealed subtleties in temperature distribution across the object's surface. Using its infrared sensitivity, Webb measured the thermal emission of different regions, mapping areas of varying heat retention. These data suggested that 3I Atlas had a layered internal structure, perhaps a dense, rocky core surrounded by porous ice. Such internal differentiation implied a history of heating and cooling cycles, possibly while orbiting close to its original star before ejection. If true, it would indicate that planetary processes similar to those in our solar system occur throughout the Milky Way. Another striking aspect of the Webb image was the trail of fine dust following 3Y Atlas. Analysis showed that the dust particles were smaller than those typically seen in solar system comets, implying they were formed in a different environment, perhaps under lower gravitational compression or through slower accretion rates. The difference in dust properties, though subtle, was significant. It suggested that the physical conditions in other planetary systems could produce unique varieties of solid matter. This realization reinforced the notion that while the universe shares common ingredients, its recipes for creation are wonderfully diverse. For the engineers who built Webb, the success was deeply personal. Capturing a fast-moving, faint target like 3I Atlas had pushed the telescope to its operational limits. The guidance and control systems had to calculate its trajectory continuously, adjusting for motion and parallax as the telescope orbited the sun. This required an unprecedented synchronization between ground-based tracking and onboard computation. The resulting image was therefore not just an astronomical achievement, but also an engineering one. Proof that the world's most advanced observatory could adapt to the unexpected and deliver beyond its design intent. Public fascination with the event mirrored the scientific community's enthusiasm. Images of 3Y Atlas, rendered in false color infrared hues, spread rapidly through global media. For many, it was the first time they saw a tangible representation of an object from another star system. Artists and writers drew inspiration from it, imagining what worlds it might have once belonged to. The event rekindled the sense of wonder that space exploration uniquely evokes, the awareness that the universe is both vast and intimately connected, that even a grain of dust from afar can tell stories about creation and chance. As Webb continued to observe the object over several days, its trajectory revealed subtle non-gravitational forces, tiny deviations likely caused by gas jets venting from its surface. These jets, measured through shifts in position and brightness, offered insights into the internal composition and rotation of the body. The ability to detect such minute changes from over 1 million kilometers away underscored Webb's sensitivity. By studying these movements, scientists could infer not only the mass and density of 3Y Atlas, but also the distribution of its activity, painting a dynamic portrait of a living, evolving body. The broader cosmic significance of this observation lay in its confirmation that interstellar objects are not rare. In just a few years, 3 have passed through our solar system, suggesting that the galaxy is teeming with such wanderers, the discarded remnants of planet formation. Webb's capture of 3 on Atlas therefore represented more than a singular achievement. It was a harbinger of a new field of study. Future telescopes, both ground-based and orbital, will likely build upon this foundation, tracking and imaging dozens more in the coming decades. Each will carry a fragment of its home system's history, adding new chapters to our collective understanding of cosmic evolution. There was also a poetic symmetry in Webb's observation. The telescope itself, stationed far from Earth in the cold darkness of the L2 point, is a product of the same cosmic processes it studies. The silicon in its circuits, the gold on its mirrors, the carbon fiber in its structure, all forged in stars and scattered across the galaxy. When Webb captured 3Y Atlas, it was in a sense observing its own ancestral kin, the matter from which it was ultimately made. This circularity, the universe observing itself through human eyes and machines, gave the moment a profound philosophical depth that transcended data and imagery. The discovery also emphasized the importance of international collaboration in space science. No single observatory could have accomplished this alone. From early detection by Atlas to trajectory refinement by ground-based observatories and finally Webb's precision imaging, the event showcased how global cooperation can accelerate discovery. Astronomers from dozens of nations contributed to modeling, calibration, and data analysis, forming a collective effort reminiscent of humanity's shared curiosity stretching beyond borders. In that unity lay a reminder that cosmic exploration is one of the few endeavors that genuinely unites rather than divides. Technically, the Webb image of 3I Atlas demonstrated the telescope's versatility. Designed primarily to observe faint galaxies and exoplanet atmospheres, Webb proved equally adept at tracking dynamic targets within our solar system. Its adaptive optics and software pipelines, initially optimized for deep field imaging, were reconfigured to handle the object's apparent motion. This adaptability expanded Webb's scientific range, positioning it as a multi-purpose observatory capable of investigating everything from the universe's infancy to fleeting interstellar guests. The achievement reflected a broader truth. In science, flexibility is as vital as precision. As the data from Webb continued to flow, models of 3I Atlas grew increasingly sophisticated. Scientists built three-dimensional simulations showing how its surface evolved as it approached and retreated from the sun. They estimated how solar radiation pressure altered its spin, how sublimating gases sculpted its faint tail, and how interstellar dust adhered to its surface during its long journey. Each refinement brought a deeper appreciation for the complexity of even a small, icy rock adrift in the cosmos. The object's simplicity was deceptive. Within its few cubic kilometers lay the record of countless cosmic events. One particularly fascinating insight came from the ratio of isotopes detected in the object's ices. Webb spectrometers measured variations in deuterium and carbon isotopes, atomic fingerprints that differ between star systems. These isotopic ratios hinted that 3I Atlas originated in a region richer in heavy elements than our own solar system, possibly around a younger, more active star. Such findings opened new possibilities for tracing interstellar objects back to their stellar nurseries, effectively using them as messengers to map galactic chemical diversity. For the first time, astronomers had the tools to study another system's chemistry without leaving our own. Throughout this process, the public watched with growing fascination as NASA and ESA released successive images and analysis updates. The sense of witnessing a cosmic first resonated deeply. The realization that, for all our technological prowess, humanity remains a small, curious observer in a universe filled with mysteries that occasionally drift close enough to glimpse. Webb's image of 3I Atlas reminded everyone that exploration need not always mean reaching out physically. Sometimes it is enough to look with precision and wonder. The night sky had long been a canvas of speculation, but with the capture of 3Y Atlas by the James Webb Space Telescope, that canvas came alive in a way that even seasoned astronomers struggled to articulate. What Webb had accomplished was not merely another observational feat, it was a shift in perception, a revelation that the universe itself could be engaged with, not just as a distant expanse, but as an interactive landscape of tangible messengers. Each pixel in that faint image was laden with information, each wavelength a cipher from another sun, another origin story, another possibility. Even before Webb's gold mirrors turned toward it, 3I Atlas had already been a tantalizing enigma. Its trajectory defied conventional expectations, entering the solar system on a path so steep that early calculations had to be repeatedly refined to ensure accuracy. It came not as a comet trailing a spectacular plume, nor as a dull rock wandering aimlessly, but as something between the two, a hybrid that resisted easy classification. That defiance of categorization became part of its allure. Astronomers love anomalies. They are the universe's way of saying, look closer. And when Webb finally did, the cosmos rewarded that curiosity tenfold. The telescope's sensors, designed to detect the most distant galaxies, were suddenly focused on a fleeting traveler within our own stellar neighborhood. This shift in observational scale required a unique blend of patience and precision. Engineers had to compute exact timing so that Webb's slow, deliberate movement could synchronize with the blistering velocity of an object racing through space at nearly 60 kilometers per second. That synchronization, measured to fractions of a second, was essential for clarity. For a machine stationed a million miles from Earth, even the smallest misalignment could turn a target into a blur of meaningless photons. Yet Webb's control systems, fine-tuned after years of testing and calibration, performed flawlessly. The image that emerged was crisp enough to detect gradients in the object's faint glow, gradients that told a story about its structure and composition. The revelation that 3I Atlas contained complex hydrocarbons reverberated through every corner of the scientific community. Organic molecules, the precursors of life, had been found before in comets from our solar system. But to detect them in an interstellar object implied something monumental, that the chemistry of life might not be a local phenomenon but a universal one. The idea that amino acids, simple sugars, and hydrocarbons could form independently around different stars expanded the framework of astrobiology. Life, or at least the potential for it, might not be exceptional. It could be an inevitable consequence of cosmic chemistry repeating itself across the galaxy, a pattern woven into the fabric of creation. That realization carried a quiet, emotional resonance. Humanity had always looked outward with questions that bordered on existential. Are we alone? Is life elsewhere possible? With Webb's image of 3I Atlas, the answer tilted ever so slightly toward affirmation. It wasn't proof of life, of course, but it was a step closer. A fragment of evidence suggesting that the building blocks are not confined to one star system. Somewhere, perhaps orbiting a distant sun, those same molecules might have coalesced into something breathing, something aware. And for the first time, that possibility didn't seem speculative. It felt statistical, almost inevitable. The composition of 3I Atlas challenged traditional planetary formation models. Analysis of its reflectivity and emission spectra revealed that it contained silicates and metallic grains intermixed with ices, an unusual combination indicating that it had formed in a region of its parent system where both heat and cold alternated cyclically. That alone hinted at a dynamic birth environment, perhaps a protoplanetary disk around a binary star where gravitational perturbations continually stirred material between hot and cold zones. Such systems are inherently unstable, and instability often breeds ejection. At some point, 3I Atlas was likely flung out by gravitational interactions, cast adrift into the void between stars. Its exile became its destiny, and millions of years later, that exile brought it here. Webb's imaging capabilities added unprecedented nuance to the understanding of that journey. The faint diffused glow surrounding the object was not uniform. Subtle asymmetries hinted at the direction of solar radiation pressure and outgassing activity. These variations were used to model its spin, revealing that 3I Atlas rotated in a slightly tumbling motion, suggesting an irregular shape, not spherical but elongated, perhaps spindle-like. This shape was consistent with what scientists expected from interstellar debris subjected to collisions and erosion. Over eons, micrometeorite impacts, radiation, and temperature shifts had carved away its symmetry, leaving behind a rugged relic of cosmic history. What fascinated researchers even more was the surface texture inferred from the light-scattering properties. The reflectance pattern suggested a crusted surface, coated in layers of refractory dust that insulated the more volatile ices beneath. This mantling process is typical of comets that have undergone repeated heating, but in this case, it occurred outside any star's sustained warmth. Instead, the mantle may have formed from exposure to interstellar cosmic rays, slowly carbonizing the surface and darkening it. That carbonization was visible in the Webb data, giving the object its characteristic reddish hue in the infrared spectrum. It was the color of ancient chemistry, a patina left by time and distance. In a way, Webb had not just captured a rock, but an autobiography written in atoms. Each layer, each molecule carried a record of its environment, the star it once orbited, the radiation it endured, the collisions that scarred it, the temperatures that shaped its core. And reading that autobiography required no words, only light. Webb's detectors translated those light patterns into data that when decoded became a narrative older than Earth itself. As the telescope continued its observation campaign, it became clear that 3Y Atlas was losing mass at a measurable rate. The gases escaping from its surface left a thin trail extending thousands of kilometers. By analyzing how the light from the sun refracted through that tail, scientists could identify its composition in detail. They found traces of water vapor, ammonia, carbon monoxide, and carbon dioxide, volatile compounds that suggested the object had preserved much of its primordial material since formation. Unlike comets within our system, which undergo periodic heating and loss, 3I Atlas had remained in cryogenic preservation for billions of years, untouched until its chance encounter with our sun. Its tail was therefore a revelation, a release of ancient material into our solar system for the first time. In those escaping vapors lay another extraordinary opportunity to study the chemical fingerprint of another star's protoplanetary disk without leaving our own. The ratios of isotopes within the gases could reveal the temperature and pressure conditions under which they formed. Already, preliminary analysis indicated that 3Y Atlas originated in a colder environment than our solar system's outer regions. That detail mattered because it implied a different distribution of elements and volatiles across star-forming regions in the galaxy. Each new interstellar object observed could thus serve as a sample from another corner of the Milky Way, collectively building a mosaic of galactic chemistry. For cosmologists, this was a breakthrough parallel to what the Apollo missions had done for lunar science. Just as moon rocks had rewritten the history of our solar system, the Webb image and spectral data from 3Y Atlas had the potential to rewrite our understanding of planetary systems beyond it. It was as though nature had sent us a message in a bottle from across the cosmic sea, and Webb was the first to unseal it. While much of the public attention focused on the beauty of the image, the deeper significance resided in what it symbolized for methodology. Observing interstellar objects requires a fundamental shift in how astronomy is practiced. These bodies move fast, appear suddenly, and vanish within months. Traditional observation campaigns planned years in advance are ill-suited to such spontaneity. The successful imaging of 3Y Atlas by Webb demonstrated that adaptability, coordination, and rapid response protocols could bring precision to chaos. It was a triumph not just of optics, but of logistics. The ground-based telescopes that initially discovered and tracked 3Y Atlas were part of a global network that monitored near-Earth objects for potential threats. Their collaboration with Webb's team turned what might have been a brief curiosity into a coordinated scientific event. Data from radar observations, optical tracking, and photometry fed into Webb's targeting system. This synergy between Earth and space telescopes represented a new paradigm of observation, a distributed, dynamic system capable of responding to transient cosmic events with near-immediate precision. And that perhaps is where 3I Atlas most profoundly altered astronomy. It reminded scientists that the universe is not a static stage, but a living, changing theater. New actors can appear at any moment, and readiness determines discovery. In the wake of Webb's success, agencies began planning how future observatories could emulate this agility. Automated tracking systems, machine learning algorithms for rapid classification, and dedicated alert channels for interstellar candidates became priorities. 3I Atlas had not only expanded our understanding of the cosmos, it had altered how we prepare to meet it. As the weeks passed, the object's changing brightness revealed subtle fluctuations, which hinted at complex rotation patterns. Using this variation, astronomers deduced that it was not spinning uniformly but wobbling, its axis shifting chaotically. This tumbling motion was likely the result of past impacts or outgassing asymmetries. That irregular spin created differential heating, producing localized jets that further altered its rotation, a feedback loop of motion and erosion that would eventually reshape it entirely. For planetary scientists, this dynamic behavior offered a glimpse into how small bodies evolve under stress, both within and beyond solar systems. At the same time, the faint halo surrounding 3I Atlas served as a lens through which scientists could study the solar wind itself. As particles from the sun interacted with the outgassed material, they generated subtle electromagnetic signatures detectable by Webb's instruments. This interaction effectively turned the object into a miniature laboratory for plasma physics, allowing researchers to analyze how solar particles behave when encountering alien material. The findings would later inform models of stellar wind interactions across different star types, contributing indirectly to exoplanet research. Every observation seemed to unfold another layer of interconnectedness. The chemistry of 3I Atlas informed theories about star formation. Its motion refined gravitational models. Its dust provided insight into particle physics. Its trajectory even contributed to our understanding of the galactic environment surrounding our solar system. In the cosmic web of knowledge, this single object touched multiple strands at once, linking disciplines that seldom intersected so directly. Philosophically, the moment carried an even greater weight. Humanity had built a machine capable of peering deep into time, designed to study galaxies billions of light years away, and yet it was now being used to study something passing briefly through our neighborhood. There was poetic symmetry in that, a reminder that significance in the cosmos is not measured by distance or scale, but by connection. Webb had shown that the same technology that reveals the ancient light of the universe could also capture the immediate whispers of a transient visitor. It was as if the cosmos itself had orchestrated the event to remind us that grandeur and intimacy coexist in the same sky. The narrative of 3Y Atlas became one of continuity, not isolation. In its chemistry, structure, and movement lay echoes of universal processes that transcended boundaries. Each atom of carbon or oxygen within it had once been forged in a star, just like those within us. Its passage through our solar system was a cosmic handshake, a silent acknowledgement that the materials of existence circulate endlessly between systems, planets, and beings. For many astronomers, there was a personal sense of wonder. The Webb Telescope, in its pristine silence at the Lagrange point, was a symbol of pure observation, detached yet profoundly connected. Its image of 3Y Atlas represented the fusion of art and science, a portrait of transience rendered in eternal precision. Unlike the iconic Hubble images of nebulae or galaxies, this was not a scene of grandeur but of intimacy. A lone wanderer, fragile and fleeting, immortalized in infrared light. It was the kind of image that transforms scientific data into emotion, numbers into narrative. The long exposure times Webb used to capture 3Y Atlas also recorded faint background stars distorted by the object's movement. In those subtle streaks of light lay a visual metaphor, the universe in motion, unceasing, unpredictable, yet patterned. Every streak was a reminder that everything moves. Stars orbit the galactic center, galaxies drift through space, and even the space between them expands. Against that vast dynamism, 3I Atlas was a traveler, and we were its brief hosts. From an observational standpoint, Webb's data opened possibilities for understanding how interstellar matter interacts with the heliosphere, the vast bubble carved by the solar wind around our system. As 3I Atlas entered and exited this boundary, the way its coma behaved offered insights into the density and composition of the interstellar medium beyond. Such data were impossible to gather directly, making this event an invaluable probe of the invisible frontier that separates our solar system from the rest of the galaxy. Even as the telescope continued collecting data, theorists began integrating its findings into broader cosmological models. If interstellar objects like 3I Atlas are common, then each solar system must contribute a steady outflow of debris to the galaxy, a continuous exchange of material. Over billions of years, these interactions could homogenize the galaxy's chemical composition, ensuring that the seeds of planetary formation and potentially life circulate widely. In essence, 3Y Atlas was not an anomaly, but part of a cosmic cycle, the same cycle that eventually produces stars, planets, and observers. The Webb image also carried subtle implications for technology itself. Capturing and analyzing something so fleeting required advancements in data compression, real-time calibration, and remote reprogramming. The success of this observation would likely influence future space missions. The techniques refined for 3I Atlas could one day be used to intercept and study interstellar objects directly, perhaps even sample them. Concepts for fast response probes, propelled by solar sails or compact ion drives, were already being revisited in light of Webb's success. Humanity was beginning to imagine not only observing such visitors but meeting them in flight. Amid all the scientific discussion, there was also an undercurrent of reflection, a recognition of scale and impermanence. The universe operates on timescales that dwarf human existence, yet through ingenuity, humans had managed to catch a moment that would otherwise have passed unseen. 3. Atlas had likely traversed interstellar space for millions of years, and for a few days or weeks it became a subject of human fascination. The odds of such a convergence, of its trajectory intersecting ours, of our instruments being ready, were astronomical in every sense, yet it happened. That improbability was not lost on anyone who studied the image. It served as a reminder that even in a universe of incomprehensible vastness, moments of connection still occur. The delicate balance between technical precision and poetic resonance defined the legacy of Webb's capture. The telescope itself functioned flawlessly, maintaining cryogenic stability and vibration control while tracking a target moving unpredictably. The data transmission, analysis pipelines, and calibration routines worked seamlessly, despite pushing the observatory to operational limits. For mission control teams, it was an affirmation of years of effort. For scientists, it was an expansion of possibility. For everyone else, it was a vision of the infinite made real. In later observations, Webb detected faint traces of cyanide compounds in the object's spectrum, a surprising discovery that deepened its intrigue. Cyanides are volatile and fragile, easily destroyed by radiation. Their presence indicated that the object's interior had remained shielded from cosmic rays for eons. That meant its crust, though thin, was extraordinarily effective at protection. Studying this natural shielding effect could one day inform how spacecraft are designed to endure long interstellar journeys. 3I Atlas unintentionally was teaching us how to travel the spaces it had long crossed alone. Each dataset Webb returned was another piece of a puzzle that would take years to assemble fully. The photometric curves, the spectral maps, the compositional analyses, all were archives of information waiting for future insights. Decades from now, when technology has advanced and theories have matured, researchers will likely revisit this data and find new meanings hidden within it. That enduring value transformed the observation into more than a fleeting success. It became a foundation for generations of inquiry. As the object moved beyond the reach of Webb's instruments, fading into the background of interstellar night, the data it left behind continued to illuminate new pathways of thought. Scientists began to question what other kinds of interstellar matter might pass through unnoticed. Microscopic grains, dormant microbial spores, frozen amino acid chains. If objects like 3I Atlas are common, then so too might be the transfer of organic material between systems. That concept, known as panspermia, gained renewed scientific weight. The idea that life's ingredients might traverse the galaxy not as an anomaly, but as a natural process reshaped the philosophical landscape. Life in this view was not a singular emergence, but a repeating pattern, a cosmic rhythm echoing wherever conditions align, and all of it traced back to a single image. Faint light from a passing traveler, preserved by the golden eyes of a telescope that itself floated in the void. The symmetry of that moment was profound. Humanity, born from stardust, had built a machine of stardust to look upon another fragment of stardust, and in doing so, had glimpsed the continuity of creation. The beauty of Webb's capture of 3Y Atlas lay not in spectacle, but in subtlety. There were no brilliant colors or dramatic tales stretching across the sky. What it offered instead was quiet revelation, the kind that rewards patience and contemplation. It showed that discovery is not always about grandeur. Sometimes it is about attention, the willingness to look closely enough to see meaning in the faintest light. Long after the data collection ended, artists and scientists alike continued to interpret what it meant. To some, 3I Atlas represented cosmic loneliness, a wanderer between stars, eternally adrift. To others, it symbolized connection, proof that the distances between systems are bridged by material exchange. Both interpretations were true, and together they formed a deeper truth, that the universe is simultaneously solitary and communal, vast yet intimate. Every aspect of the event reinforced the notion that knowledge is born from convergence of technology, curiosity, timing, and luck. The Webb Telescope was the product of thousands of minds working across decades, each contribution an act of faith in the unseen. 3I Atlas was the product of gravitational chaos, a random traveler shaped by forces indifferent to observers. Yet somehow, across light years and lifetimes, their paths intersected. That intersection became a moment of meaning, proving once again that the universe, however indifferent, allows for wonder. Even as new discoveries await, the image of 3I Atlas remains singular. A quiet triumph that distilled the essence of exploration, the pursuit of understanding through light. It captured not just an object but a philosophy, that seeing is the first act of knowing, and knowing is the first step toward belonging in the cosmos. The Webb Telescope, gazing into the darkness, had reached out to something beyond all maps and brought it into the circle of human awareness. In that instant, the distance between stars felt smaller, and the universe, the light that reached Webb's golden mirrors from 3I Atlas, had been traveling for hours across the void, each photon carrying a story of its encounter with the alien object's surface. It struck the telescope's detectors with such faint intensity that even the most sophisticated instruments had to strain to interpret its message. Yet in those delicate signals lay the fingerprints of a world not born under our sun. For scientists, it was akin to deciphering a whisper across an ocean, fragile, fleeting, but profound in meaning. The realization that humanity could now capture in real time the detailed light signature of matter forged in another stellar nursery was an intellectual and spiritual milestone. At first glance, 3I Atlas was not extraordinary in shape or brightness. What made it unique was what it represented. A fragment of cosmic history traveling between stars, unbound, unclaimed. Its journey had likely begun before human civilization, perhaps even before the Earth had cooled enough to form oceans. It was a relic from an ancient process of planetary construction in some distant system, a discarded shard propelled by gravitational turbulence into exile. Now, after countless revolutions around the galaxy, it had wandered into the embrace of our solar system, where a telescope built by descendants of stardust waited to greet it. That moment of intersection, chance meeting engineering, encapsulated the entire essence of exploration. The Webb data revealed a depth of complexity that exceeded all expectations. Each wavelength in its spectrum carried layers of encoded chemistry, allowing scientists to reconstruct the object's mineralogy and thermal behavior. In the near-infrared range, the signals showed deep absorption features that corresponded to frozen methanol and ammonia hydrates, while mid-infrared readings indicated a silicate framework beneath the icy surface. The combination of these materials implied that 3I Atlas had once existed in a region with fluctuating thermal zones, possibly orbiting a young star undergoing violent outbursts. Those heating cycles would have allowed both rock and ice to coexist, a hallmark of transitional zones within protoplanetary disks. That coexistence of extremes fascinated planetary theorists. In our solar system, the boundary between rocky and icy bodies lies near Jupiter's orbit, where the so-called frost line separates inner heat-scorched planets from outer ice-rich ones. If 3I Atlas originated in a similar region around another star, its composition could offer insight into where that system's frost line once existed. By comparing isotope ratios and volatile distributions, astronomers began to reverse engineer its home environment, an act of forensic cosmology. In essence, Webb's image allowed humanity to peer indirectly into the birthplaces of alien worlds. Further analysis showed faint but recurring infrared emissions that pulsed rhythmically over the observation window. These fluctuations suggested localized jets of sublimating gases venting from beneath the surface. Such jets not only altered the object's trajectory, but also exposed fresh material, giving scientists a look into its untouched interior. The ratio of carbon to oxygen compounds in these emissions was strikingly different from typical solar system comets, hinting at a unique chemical fingerprint tied to another stellar lineage. It was as though each interstellar visitor carried a passport stamped with the history of its origin, and Webb had just deciphered one of those stamps. The engineering precision required to track those emissions was staggering. The telescope's pointing system had to maintain alignment within arcseconds while compensating for the object's rapid apparent motion. Any deviation, even a fraction of a pixel, would have smudged the spectral readings. The Webb operations team employed predictive algorithms to anticipate minute positional changes, essentially teaching the telescope to lead the target as it would move during exposure. This dynamic tracking technique became an innovation in its own right, setting a precedent for future missions that might pursue similarly transient phenomena. While the image itself captivated the public imagination, the real treasure lay in the spectroscopy data. Infrared light is the language of molecules, and Webb was fluent in it. Through that language, the telescope translated the molecular whispers of 3I Atlas into a symphony of information, revealing not just what it was made of, but what it had endured. The subtle widening of certain absorption lines indicated the presence of amorphous ice, a sign that the object had experienced rapid cooling after being ejected from its home system. Other features pointed to trace metallic oxides, perhaps remnants of the original star's protoplanetary environment. Each spectral line was a fossil, and together they formed a geological narrative written in light. The more scientists analyzed the data, the clearer it became that 3Y Atlas was no simple comet. Its density estimates, derived from its observed activity and trajectory deflection, placed it somewhere between rock and ice, neither entirely solid nor wholly volatile. That intermediate nature blurred the boundary between asteroid and comet, challenging long-standing classification systems. In many ways, 3I Atlas became a symbol of astronomical ambiguity, reminding researchers that the universe often resists the categories we impose upon it. Its origin story grew richer with every observation. Simulations tracing its velocity vector suggested it came from a region of the Milky Way dense with young sun-like stars. Perhaps it was born in a binary system where gravitational interplay frequently ejects material into interstellar space. If so, 3I Atlas was not a solitary orphan but a representative of a vast diaspora of matter flung from its birthplaces across the galaxy. Every interstellar object we encounter, therefore, is not an anomaly but part of a galactic exchange, a slow, continuous trade of dust, ice, and stone between star systems. That idea reshaped the way astronomers thought about planetary migration. Instead of isolated systems, the Milky Way began to look like a vast ecosystem of shared material. Just as pollen drifts between flowers on the wind, cosmic debris travels between stars, cross-pollinating planetary disks with new ingredients. Some of those ingredients may one day seed other worlds with the precursors of life. The Webb image of 3I Atlas thus symbolized not isolation but interconnection, a quiet affirmation that the galaxy itself behaves like a living network, circulating its raw materials endlessly. In that sense, 3I Atlas was more than a curiosity. It was evidence of the galaxy's memory. The atoms composing it had been part of older generations of stars, recycled through supernova explosions, recombined in molecular clouds, and sculpted into planets before being ejected again. By the time it crossed paths with Webb, those atoms had participated in a chain of creation and destruction billions of years long. To observe them was to glimpse a piece of the Milky Way's autobiography, one chapter among countless others written in rock and ice. There was an unexpected intimacy to the observation as well. The photons reflected off 3I Atlas had last touched its surface mere hours before they entered Webb's instruments. In that brief interval, they had crossed millions of kilometers, passing through the gravitational fields of planets and the faint haze of interplanetary dust. When they finally struck Webb's mirrors, they carried not just data, but immediacy, a direct connection between human-made technology and a cosmic traveler that would never return. The encounter lasted only weeks, but it created a bridge across light years. Within the data lay subtleties that defied initial interpretation. Slight polarization effects in the reflected light hinted at a layered composition, possibly alternating strata of compact ice and fine dust. That stratification might have resulted from cycles of sublimation and refreezing during its early life in its native system. The process would have sealed organic molecules within the layers, preserving them from radiation. If future missions ever managed to sample such objects, those buried compounds could reveal pristine examples of prebiotic chemistry, the same kinds of molecules that once seeded Earth's primordial oceans. The philosophical implications grew as profound as the scientific ones. For centuries, humanity had viewed the stars as distant and unreachable, their planets as subjects of speculation. Now, through the simple act of observation, a fragment from another system had crossed into ours and shared its secrets. It was not us reaching outward this time, but the universe reaching in, offering a tangible reminder that we are part of its continuous narrative. The boundaries we draw between here and there, between ours and theirs, are human inventions. The cosmos recognizes no such divisions. The timing of Webb's observation also carried poetic resonance. At a moment in history when humanity grappled with its own divisions and distractions, the universe offered a reminder of unity through perspective. For a few nights, scientists and laypeople alike looked at the same image and felt the same awe, that peculiar blend of insignificance and belonging that only the stars can provoke. It was as if the telescope had momentarily silenced the noise of the world to let the cosmos speak. As data continued to pour in, thermal modeling revealed fascinating behavior. 3. I-Atlas did not heat uniformly as it approached the sun. Instead, certain regions warmed and released gas more rapidly, while others remained cold and dormant. This uneven thermal response suggested that its composition was patchy, perhaps the legacy of heterogeneous accretion during its formation. Some zones contained dense, refractory material that absorbed sunlight slowly, while others harbored volatile, rich pockets that erupted in sudden bursts. These eruptions not only sculpted its faint tail, but also produced minute torques that altered its rotation. In effect, 3 I-Atlas was reshaping itself under the gentle hand of sunlight. Such self-altering behavior is common among comets, but in an interstellar context, it acquired deeper significance. Each burst of gas revealed a microcosmic drama of change, a miniature echo of the processes that shape entire worlds: heat, motion, and decay, the same triad that governs everything from asteroids to galaxies. Webb's sensors, sensitive to the faintest thermal shifts, turned those invisible transitions into data, transforming ephemeral reactions into permanent knowledge. Among the most striking revelations was the detection of silicate emission features resembling those found in protoplanetary disks. These forsterite and enstatite signatures, minerals formed at high temperatures, were unexpected in a body that had spent eons in deep freeze. Their presence indicated that 3 Y-Atlas had likely formed near its parent star before being scattered outward. This discovery painted a dramatic portrait of its past. Once orbiting close enough to a star to melt and crystallize minerals, later hurled outward into the cold, then cast adrift across interstellar space. It was a life story of extremes: birth in fire, exile in ice. For scientists, this duality encapsulated the essence of cosmic evolution: creation and destruction, warmth and cold, motion and stillness. The same forces that govern stars also sculpt the smallest grains of dust. In studying 3 I-Atlas, humanity glimpsed those universal rhythms in miniature. It was as though nature had compressed the entire life cycle of a planet into a single wandering relic. The public fascination that followed Webb's capture of 3 I-Atlas reignited cultural interest in astronomy. Images spread across media platforms, often colorized to reveal infrared nuances invisible to human eyes. People saw not a smudge of light, but a symbol of curiosity, persistence, and cosmic kinship. Artists rendered the object as a glowing wanderer sailing through darkness, while musicians composed pieces inspired by its lonely journey. For a time, science and art spoke the same language, united by wonder. Within research circles, debates flourished. Some argued that the object's composition hinted at similarities with outer solar system bodies, suggesting a kind of universality in planet formation. Others insisted the differences were too stark to be coincidental, evidence of diverse pathways by which systems evolve. These discussions were not disagreements but expansions of possibility. Every interpretation opened new questions. How many such objects pass unnoticed each year? What can they teach us about planetary migration? Could they one day be harvested as interstellar archives? The excitement lay not in definitive answers, but in the proliferation of new ideas. As the object drifted away, receding from the sun, Webb continued to observe it intermittently, pushing its instruments to the edge of sensitivity. The diminishing brightness tested the limits of detection, but the telescope persisted, catching the faintest echoes of reflected light. Even as 3I Atlas faded into anonymity, the data persisted, a digital fossil of its presence. For those who had spent months preparing and coordinating the observation, the fading signal was bittersweet. Yet there was satisfaction in knowing that for the brief time it was visible, nothing about it went unseen. The success of Webb's observation also influenced mission planning for future telescopes. Engineers began to envision observatories capable of faster repositioning and wider field coverage to catch such transient visitors. The possibility of deploying small autonomous telescopes at various points in the solar system to triangulate interstellar trajectories gained serious traction. 3I Atlas had demonstrated that with coordination and precision, even the most fleeting cosmic travelers could be studied in remarkable detail. Humanity had learned to listen to the whispers between stars. The philosophical ripples extended into discussions of cosmic origin and purpose. Some thinkers saw in 3I Atlas a metaphor for humanity itself, a traveler through vastness, carrying remnants of its home, shaped by encounters destined to continue onward. Just as the object's surface bore scars of its journey, human civilization bears the marks of its passage through time. The telescope's image, therefore, became more than a scientific artifact. It was a mirror of endurance and motion. What made the event especially poignant was its temporality. The object appeared, was studied, and then vanished, perhaps forever. Unlike galaxies or nebulae that remain constant subjects for generations, interstellar visitors remind us that observation is a race against time. Every photon captured is a victory over impermanence. Webb's image of 3I Atlas was not just a record of a celestial body, it was a triumph of timing, of being ready when the universe offers something transient and unrepeatable. The data would later help refine models of galactic dynamics. By studying the direction and speed of 3I Atlas, astronomers could map gravitational flows in our region of the Milky Way. Interstellar objects serve as natural probes of galactic structure, moving under the combined influence of multiple stellar systems. Their trajectories act like invisible threads tracing the contours of gravitational fields. Thus, from a single observation, scientists could infer the subtle architecture of our cosmic neighborhood. Another unexpected insight came from the way the object's coma, the cloud of gas surrounding it, interacted with sunlight. Polarization measurements showed that the dust particles were unusually small and uniformly distributed, unlike the diverse grains in typical comets. This hinted at differences in how dust aggregates form in other systems. If such dust tends to be finer and more cohesive elsewhere, it could affect everything from planetary surface formation to atmospheric retention. In this way, 3I Atlas indirectly contributed to our understanding of exoplanet habitability. When the last data packets from the James Webb Space Telescope's observation of 3I Atlas were received and logged, the sense of closure among the mission scientists was curiously incomplete. The object had already retreated beyond the reach of Webb's most sensitive instruments, its faint glow dissolving into the background tapestry of interstellar space. Yet the silence it left behind seemed to resonate with more meaning than any burst of data. It was the silence of a chapter closing, not with finality, but with the kind of lingering curiosity that only deepens with understanding. 3I Atlas had come and gone, leaving behind a trail not of dust, but of questions that would ripple across astronomy for decades. The first of these questions was almost philosophical. How much of what we had seen in 3I Atlas was typical, and how much was singular? The universe rarely reveals whether an event is common or unique. A single interstellar visitor can be either the first of countless others or a solitary anomaly from an unrepeatable process. Without context, one cannot know. Yet even that uncertainty was precious. It reminded astronomers that discovery often begins in ignorance, that the value of 3I Atlas was not in what it concluded, but in what it provoked. The Webb data contained subtleties that would take years to fully analyze. Deep in the infrared spectrum, faint absorption lines hinted at compounds not previously identified in any solar system comet. These were long-chain organosilicon molecules, rare in nature and usually associated with high-temperature chemical reactions. Their presence within an icy interstellar body raised new possibilities. Perhaps in the fiery birth throes of its original system, 3I Atlas had been forged closer to its star than once believed. If that were true, its ejection must have been extraordinarily violent, a slingshot through gravitational chaos powerful enough to fling it from warmth to eternal cold. In that sense, 3I Atlas was more than a fragment of another world. It was the frozen aftermath of cataclysm. The energy that cast it into exile had probably disrupted an entire planetary neighborhood, scattering asteroids and comets like sparks from a cosmic forge. What Webb captured, then, was not merely a visitor but a survivor, a remnant of destruction that had transformed into an emissary. The violence of its birth had delivered it to the serenity of deep space, and through chance, to our gaze. Among the most remarkable aspects of Webb's observation was the discovery of distinct layering within the object's crust. By studying how infrared light was absorbed and reflected at different wavelengths, scientists could infer that the outer surface was composed of alternating bands of material with varying densities. The topmost layers appeared porous, possibly due to repeated cycles of heating and cooling during its interstellar journey. Beneath that, denser bands of ice and dust alternated like geological strata, recording epochs of exposure and dormancy. It was, in essence, a time capsule in physical form, a stratigraphy of the cosmos. One particularly intriguing layer showed spectral signatures consistent with olivine crystals, which typically form in the presence of molten silicates. Their existence within an icy body suggested that at some point in its early life, 3I Atlas had undergone internal heating. That heat could have come from radioactive decay or tidal stresses during a close approach to its parent star. Either scenario implied a more complex geological past than previously imagined for interstellar wanderers. It suggested that 3Y Atlas, far from being a simple chunk of debris, might once have been part of a larger, differentiated world, perhaps the fragment of a protoplanet destroyed during formation. To contemplate that possibility was to see the object not as a solitary stone adrift in space, but as the remnant of a lost history. Somewhere long ago, a system had experienced the same chaotic collisions that once shaped our own. Planets coalesced and shattered, orbits shifted, atmospheres formed and vanished. Out of that turbulence came a small survivor, flung outward with enough velocity to escape the gravitational reach of its star forever. For millions of years it drifted between suns, carrying within its layered body the memory of that forgotten world. When Webb's mirrors caught its faint glimmer, humanity was essentially reading a page torn from another planet's storybook. The precision with which Webb's instruments recorded the object's spectral and thermal properties astonished even the engineers who had built them. Each sensor array had been designed for steady targets, distant galaxies, exoplanet transits, nebulae, objects that changed slowly, predictably. 3I Atlas was the opposite. It moved rapidly across the sky, dimmed unpredictably, and rotated irregularly. Yet Webb's algorithms adapted, synchronizing exposures and compensating for movement with breathtaking finesse. The resulting dataset was not only scientifically valuable, but also an operational triumph. It demonstrated that a telescope built to peer across cosmic epochs could also chase the fleeting messengers that wander through them. For planetary scientists, the implications extended beyond chemistry. The internal structure implied by Webb's data suggested a degree of cohesion stronger than expected. The object did not appear to fragment or shed large pieces despite its outgassing, implying a nucleus bound by both gravity and structural integrity. This combination pointed to a compact, possibly sintered composition, where ice and rock had fused together over time into a rigid matrix. Such material strength could explain how it had survived countless micrometeorite impacts during its long voyage. It was, by every metric, a testament to endurance. Even the way it reflected light told a story of its resilience. The scattering pattern of photons across wavelengths indicated a surface coated with fine-grained particles, some less than a micron in diameter. These ultrafine grains, likely formed from the slow erosion of cosmic radiation, gave the object a velvety sheen when viewed in infrared. They also acted as insulation, reducing sublimation and preserving the volatile ices beneath. Over millennia, this layer had evolved into a protective skin, a kind of cosmic armor against time. Astrobiologists were captivated by the organic chemistry implied in the spectra. The detection of nitrogen-bearing molecules, including nitriles and simple amines, provided further evidence that interstellar objects carry prebiotic materials. These compounds are known to react under certain conditions to form amino acids, the basic units of life. While 3I Atlas itself was far too cold and barren to nurture such chemistry actively, it might have carried these ingredients across the galaxy for billions of years. The notion that interstellar travelers like it could be the couriers of life's raw materials was no longer speculative, it was measurable. This concept reframed humanity's understanding of panspermia, not as myth or metaphor, but as an observable process. 3I Atlas became proof that the universe is in constant chemical dialogue with itself. Star systems exchange material, and within that exchange lies the potential for continuity. The seeds of life drifting invisibly through the spaces between suns. When Webb detected those organic signatures, it wasn't just documenting a rock. It was documenting communication between worlds. Even more astonishing was the faint magnetization inferred from the polarized light data. The dust particles in the object's coma aligned slightly with the solar magnetic field, a phenomenon that could only occur if the grains themselves carried residual magnetism. That residual field, frozen in during the object's formation, provided a snapshot of the magnetic environment of its home system. By comparing it to measurements within our own solar system, scientists could infer differences in stellar activity, magnetic field strength, and disk dynamics across regions of the galaxy. In essence, 3I Atlas carried within it the magnetic fingerprint of another sun. The emotional resonance of such findings was difficult to quantify. To think that a piece of alien matter, once circling an unknown star, could now reveal that star's invisible forces to human eyes, it was both humbling and exhilarating. In a single stroke, Webb had turned the universe from a distant abstraction into something tactile, almost intimate. The space between stars was no longer empty. It was a corridor filled with travelers, each bearing silent testimony to their origins. As scientists reconstructed the likely history of 3Y Atlas, new layers of mystery emerged. Its velocity relative to the Sun was slightly slower than expected for interstellar objects, suggesting that its ejection had occurred not through violent collision, but through a gentler gravitational resonance. That nuance changed the tone of its story. Instead of a chaotic birth from catastrophe, perhaps it had been nudged slowly outward over eons, migrating from the outskirts of its home system until one day, gravity released its grip entirely. There was poetry in that idea. The notion of a world quietly letting go of one of its fragments, sending it into eternity. The trajectory of 3I Atlas through our solar system was steep and fleeting. Yet during that brief passage, its interaction with solar radiation created a phenomenon known as radiation-induced torque, which subtly altered its spin rate. Webb's high-cadence imaging allowed scientists to measure this change, observing how the object's rotation accelerated as it approached the Sun. This acceleration provided crucial data about its shape and mass distribution, further confirming its elongated structure. The interplay between light and motion between photons and momentum was a demonstration of the cosmic dance that governs all matter, from dust to galaxies. Beyond science, the image of 3Y Atlas became a touchstone for the public imagination. Writers compared it to a messenger, a time traveler, even a relic of cosmic memory. School children learned about it as the first clear image of an interstellar object captured by humanity's most advanced telescope. It entered cultural consciousness as a symbol of discovery without conquest, an encounter defined by observation rather than possession. There was no need to send probes or landers. The act of seeing was itself an act of communion. In university lecture halls, professors used Webb's image to teach about the unity of physics and philosophy. They spoke of entropy and permanence, of the strange balance between fragility and endurance that characterized all cosmic objects. 3. Atlas became a metaphor for resilience in motion, a body that persisted through cold, radiation, and isolation, yet carried beauty in its endurance. It reminded students that in science as in life, persistence often reveals more than brilliance. At observatories across the world, teams continued to track its fading path, Ground-based instruments detected its diminishing tail as it slipped back into darkness. The final visible traces lingered like a whisper, a reminder that even the most momentous encounters eventually dissolve into memory. But the data endured, archived in terabytes of infrared spectra and photometric curves, waiting for future generations to decode their hidden meanings. The technological ripple effects of Webb's success were already being felt. Agencies began designing next-generation infrared observatories with faster tracking systems optimized for transient targets. The algorithms developed to follow 3Y Atlas were refined into software capable of predicting and capturing interstellar objects automatically. Plans for small interceptor probes, autonomous solar-powered scouts that could launch on short notice, gained serious consideration. Humanity's relationship with interstellar visitors was evolving from passive observation to active engagement. In scientific literature, 3I Atlas would become a reference point, much like Oumuamua and Borisov before it. Yet it stood apart because of Webb's unparalleled resolution. For the first time, the universe had been seen through a lens so powerful it could transform faint passing light into a detailed chronicle of another system's history. Each new analysis added nuance to that chronicle. Temperature gradients, isotopic anomalies, trace elements. Together, they painted a portrait of a traveler both alien and familiar. One subtle but profound discovery came from the way sunlight scattered through the coma. The polarization patterns hinted at an unusual optical property known as forward scattering, where light was preferentially redirected ahead of the object's path. This effect implied that the dust grains surrounding 3I Atlas were unusually porous, almost sponge-like in texture. Such porosity is characteristic of material formed in low-gravity environments, perhaps at the outskirts of a disk where aggregation happens slowly. The finding provided another clue about its birthplace, narrowing down the kinds of systems capable of producing such matter. The team studying the observation often reflected on the fragility of timing. Had Webb been offline for maintenance, or had the object's trajectory differed by even a fraction of a degree, the opportunity would have vanished. The event underscored how discovery depends not just on technology but on circumstance, the delicate alignment of readiness and chance. The fact that both had converged so perfectly seemed almost miraculous. It was as though the universe had scheduled the meeting and humanity had simply arrived on time. Beyond the immediate science, the encounter reshaped humanity's self-image. For centuries, people had imagined interstellar space as empty, sterile, and cold. 3I Atlas defied that assumption. It revealed a cosmos alive with motion and exchange, where even the void is filled with travelers bearing the fingerprints of creation. The Milky Way was no longer a static collection of stars, but a dynamic community of systems sharing material across unimaginable distances. To live within it, humans realized, was to participate, however unknowingly, in that ceaseless circulation of matter and meaning. The final processed images from Webb, released months later, captured the object's fading trail against the background of distant galaxies. Those galaxies, ancient and immense, formed the backdrop to a story measured in hours and days. The juxtaposition was stunning, a transient visitor framed by the eternal architecture of the universe. The image reminded viewers that scale and significance are independent. A brief event can carry infinite meaning if observed with understanding. For the scientists who had devoted sleepless weeks to tracking 3I Atlas, the experience was transformative. They spoke of the strange intimacy they felt toward an object that would never know their existence. To study it was to form a kind of silent bond, a relationship grounded not in interaction but in comprehension. They had listened to its light, decoded its chemistry, and in doing so, participated in its journey, however briefly. When it faded, it felt almost like farewell. The data from the Webb Telescope had long since been downlinked, cataloged, and stored in servers across the world, yet the conversations it began had not slowed. Months turned into years, and still the observation of 3I Atlas pulsed through the scientific community like a low resonant chord that refused to fade. The object itself was now billions of kilometers away, slipping beyond the reach of even the most sensitive instruments, but its image, that delicate smear of reflected light caught by Webb's gold mirrors, continued to provoke new questions and interpretations. Every line in the spectrum, every fluctuation in brightness, seemed to conceal another layer of meaning. What most researchers agreed upon was that 3I Atlas had accomplished something almost philosophical. It forced humanity to confront the idea of cosmic continuity. It was no longer possible to think of planetary systems as isolated cradles of creation. The evidence gathered from that single observation showed that matter travels freely between stars, that elements and molecules do not remain confined to the systems that birth them. The building blocks of one world could drift into another, and through such exchanges the galaxy maintains a quiet coherence. The stars, once thought to rule over separate domains, are bound together by rivers of dust, stone, and ice. In this view, 3I Atlas was both messenger and participant. It carried not just the history of its own formation, but the shared history of stellar evolution, the recycled ash of ancient supernovae, the condensed vapors of hydrogen and carbon, the long memory of the universe itself. Each fragment of its surface was a relic of cycles too vast for human lifetimes to encompass. To study it was to engage, however briefly, with the machinery of creation at work beyond sight. The infrared data revealed one particularly striking feature: an absorption pattern consistent with sulfide minerals, specifically troilite and pyrrhotite. These minerals form under reducing conditions, meaning they require environments deprived of oxygen, conditions usually found deep within the dense midplane of a protoplanetary disk. Their presence implied that 3I Atlas had once been buried beneath layers of accreting material before being cast out into interstellar space. This buried origin was significant because it suggested that the object might have spent millions of years shielded from radiation, preserving within it chemical traces of its original nebula. That possibility opened the door to an entirely new line of inquiry. If interstellar bodies like 3I Atlas preserve primordial dust from their home systems, then by studying them, scientists can effectively sample star-forming regions without leaving the solar system. The Webb image, though a snapshot in time, was thus a bridge between here and elsewhere, a method of reading the signatures of other suns through their wandering offspring. The interdisciplinary collaborations sparked by this realization were remarkable. Astronomers, chemists, physicists, and even philosophers of science found themselves converging on shared questions. What defines an origin when matter moves so freely? Is there meaning in calling something alien if the atoms that compose it are the same as ours? The distinctions between local and foreign began to blur, replaced by a new sense of cosmic kinship. The universe, once imagined as a scattering of separate islands, now appeared as a single living ocean of circulation. Among the many insights drawn from Webb's observation was a pattern of isotopic ratios that hinted at a slightly different nuclear environment in 3I Atlas's birthplace. Its carbon isotopes showed a higher proportion of circumflex 13C than found in typical solar system material, while its nitrogen contained a lower abundance of circumflex 15N. These ratios aligned with theoretical models of star-forming regions located toward the inner edge of the galaxy, where cosmic radiation levels are lower and stellar density is higher. In other words, 3I Atlas may have originated in a region of the Milky Way far from our own, a more crowded, energetic neighborhood. If true, then the object's journey to our solar system had been one of extraordinary duration. It would have traversed the galactic arms, passing through clouds of gas and fields of dust, perhaps even brushing against the gravitational influence of other stars. Over time, its trajectory would have been altered again and again, until by sheer coincidence, it intersected our corner of space. Such a voyage stretched beyond the scale of human comprehension. For billions of years, it had drifted unobserved through the darkness, and for a few fleeting months, it reflected enough sunlight for us to see it. That fragile overlap, an instant in eternity, was what the Webb telescope captured. In the glow of that image, humanity found not only science, but story. The idea that something so ancient, so solitary, could cross our path felt almost mythic. It stirred an instinct older than civilization, the desire to assign meaning to encounters with the unknown. Yet unlike myths of the past, this story required no invention. The facts alone were enough to inspire reverence. A grain of dust from another star had entered our awareness, and through the discipline of observation, we had met it halfway. Technically, the feat was staggering. The Webb telescope's ability to track a moving object with such precision had demanded near-perfect synchronization between ground teams and automated control systems. The process involved predictive modeling on a second-by-second basis, with course corrections so fine they approached the limits of the telescope's reaction wheels. Even the solar shield, that vast multi-layered sail protecting Webb's instruments, had to maintain stability within millimeters to avoid distorting the image. Every factor, from the thermal environment to the data compression protocols, played a role. The successful capture of 3Y Atlas was as much a triumph of engineering as it was of astronomy. Yet the most profound consequences unfolded not in hardware but in thought. The Webb image forced a reconsideration of how humans relate to the cosmos. For centuries, observation had been an act of distance. The sky was something out there, separate from the observer. 3I Atlas collapsed that separation. It was tangible, measurable, close enough that its movement could be tracked night after night. Its existence turned the abstract into the intimate. It reminded observers that they, too, were part of this ceaseless interchange of matter and motion. That the atoms in their bodies might one day travel as far as 3I Atlas had. Within research circles, one theme became central: the continuity between interstellar debris and the origins of planetary life. By tracing the organic compounds detected on 3I Atlas, scientists constructed models of how complex chemistry might develop in cold environments. The presence of methanol, ammonia, and hydrocarbons suggested that ultraviolet radiation had triggered photochemical reactions on its surface, even in the dim light between stars. These reactions could synthesize precursors to amino acids and sugars. The discovery that such processes occur independently of sunlight deepened the argument that life's chemistry is universal, that it begins wherever atoms have time to combine. The implications for exobiology were profound. If such molecules form readily in interstellar space, then any planet capable of sustaining liquid water could inherit a ready-made chemical toolkit for life. This realization shifted the search for habitability from being a question of local conditions to one of inheritance. The seeds of biology might be distributed through space like pollen, waiting only for the right environment to flourish. In that sense, 3I Atlas was more than an object. It was a microcosm of potential, a vessel for the raw syntax of life. As the data continued to be studied, one peculiar anomaly drew attention. The infrared emission curves indicated a faint excess of heat on one hemisphere, too small to be caused by sunlight alone. Some hypothesized that residual radioactive elements within the object were decaying, producing internal warmth. If true, that warmth could have allowed transient pockets of liquid water within its subsurface layers during certain periods of its history. Such conditions, though fleeting, are precisely those under which prebiotic chemistry thrives. The idea that an interstellar traveler might once have harbored microscopic chemical evolution was electrifying. It transformed 3Y Atlas from a passive relic into an active participant in the story of life's emergence. The idea sparked vigorous debate. Could such an object retain enough heat to maintain liquid microenvironments? What mechanisms would prevent immediate freezing? Theoretical models suggested that porous internal structures could trap volatile gases, creating pressure differentials that temporarily liquefy ice during energy release events. These moments would be rare and brief, perhaps lasting hours or days, but across millions of years, they might allow for a cumulative chemistry of surprising complexity. Webb's data provided no direct proof of such events, but the possibility alone expanded the frontier of imagination. While the public celebrated 3Y Atlas as a symbol of cosmic wonder, within laboratories the work became meticulous and exacting. Researchers simulated its environment in cryogenic chambers, replicating the temperatures and pressures indicated by Webb's readings. They bombarded samples of ice and dust analogs with ultraviolet light to mimic interstellar radiation. The results consistently produced complex organics, dark, tar-like residues similar to those inferred from the telescope's spectra. These laboratory experiments confirmed that the processes seen on 3Y Atlas were not exotic but inevitable. Chemistry, it seemed, was the universe's most persistent storyteller. What emerged from all this inquiry was a new appreciation for transience. The universe, though vast, is not static. It is filled with motion, exchange, and impermanence. 3I Atlas reminded everyone that even stars are travelers in their own slow orbits around the galactic center, and that the material from which everything is made is in constant migration. Stability, in cosmic terms, is only an illusion born of limited perspective. The very matter of Earth will one day drift away, perhaps to be glimpsed by beings elsewhere who will study it as we studied 3I Atlas. This perspective lent a strange tenderness to the observation. The cold, impersonal void seemed less hostile when viewed as part of an ongoing circulation of substance and energy. Space was no longer an abyss, but a medium, the ocean in which everything swims. The telescope's image had not just expanded knowledge, it had redefined belonging. Humanity, too, was adrift in that ocean, not as outsiders, but as participants. As the years passed, new techniques of analysis extracted subtler details from the original Webb data. By applying machine learning to the spectral variations, researchers reconstructed a three-dimensional thermal map of the object's surface at the time of observation. This map revealed intricate temperature gradients, suggesting that the rotation of 3I Atlas was irregular, perhaps even chaotic. Its axis appeared to precess unpredictably, causing sunlight to strike at varying angles. This erratic motion could explain the uneven sublimation patterns observed in its coma, bursts of activity followed by stillness. From this, a fascinating hypothesis arose, that the tumbling motion might preserve the object's volatile materials longer than a stable spin would. By distributing heat unevenly, it prevented complete sublimation, allowing the object to retain its icy heart through repeated encounters with stars. In this sense, its imperfection became its survival mechanism. The irregularity that caused instability also ensured endurance, a paradox mirrored in nature at every scale. Meanwhile, cultural interpretations of 3I Atlas continued to evolve. Poets wrote of it as a wanderer unmoored from any sun, a metaphor for isolation and persistence. Filmmakers used it as inspiration for stories about interstellar connection and memory. Philosophers debated whether the object's passage constituted an event of significance or mere coincidence. In all these reflections, one theme recurred: the idea that meaning arises not from duration but from encounter. The brief meeting between humanity and 3I Atlas was meaningful precisely because it was ephemeral. Among astronomers, another kind of contemplation took shape. Many began to imagine the unobservable aspects of its journey, the eons spent drifting through silence, the countless star fields it must have passed, the occasional collisions with stray particles that left microscopic scars on its surface. They pictured it illuminated faintly by distant suns, then swallowed again by darkness, repeating the cycle endlessly until chance brought it near ours. In their imagination, the object's solitude mirrored the human condition. A fragment of matter traveling through time, accumulating experiences without witness, until one day it is seen and understood, however briefly. The Webb team, reflecting on the mission, often spoke of how 3I Atlas had humanized their work. For decades, telescopes had been instruments of vast ambition, studying phenomena billions of light years away. But this observation, intimate in scale, reminded them that the universe's greatest revelations are not always in distance but in proximity. To capture something moving, changing, and finite required presence, a kind of attentiveness that transcended technology. The telescope had become an extension of human patience, its mirrors a stand-in for the collective gaze of curiosity. Even as 3I Atlas disappeared into darkness, its story was far from over. The datasets continued to yield insights about dust particle physics, isotopic diversity, and molecular formation. The detection of unexpected phosphorus compounds in one of the later analyses surprised everyone, as phosphorus is a key element in biological molecules like DNA and ATP. This discovery strengthened the notion that interstellar chemistry naturally produces the essential ingredients for life. It also hinted at a uniformity in galactic evolution, that the same processes occurring around our sun are mirrored around countless others. Perhaps the most moving realization came from the acknowledgement that 3I Atlas did not need to be extraordinary to be significant. It was likely one among millions of similar bodies drifting through the galaxy. Its uniqueness lay not in its nature, but in our attention to it. The universe is filled with wonders invisible only because no one is looking at them. Webb's image was proof that seeing, when done with precision and reverence, transforms the ordinary into revelation. Scientists began to speak of interstellar visitors as part of a galactic conversation. Each new discovery would add another voice to that chorus, each spectral line another sentence in the language of matter. 3. Atlas was one of the first words in that dialogue, a greeting from afar, neither deliberate nor accidental, but inevitable. The future of astronomy would be built upon listening for such greetings, upon learning to interpret the murmurs of the universe as they pass fleetingly through our awareness. In time, the telescope that captured 3I Atlas would move on to other missions, its golden mirrors turned toward galaxies at the dawn of time. Yet the memory of that small, wayward traveler lingered. It had proven that discovery is not confined to the distant past or unimaginable future. It can happen in the immediate now, whenever light and attention meet. The Webb image of 3I Atlas was a reminder that every photon is a message, every observation a form of communion. And so, even as it drifted beyond detection, 3I Atlas continued to teach by example. It taught that the universe is porous, that boundaries dissolve under the light of understanding. It taught that fragility and endurance coexist, that a body no larger than a mountain can survive the journey between stars. It taught that meaning is not inherent in objects but arises from relationships, from the act of seeing and interpreting. For those who had followed its passage, the feeling it left behind was not of closure but of expansion. The universe felt larger, yes, but also more connected, more intimate. It was as if, through the faint glow of a distant object, the cosmos had momentarily turned its gaze back upon us. The James Webb Space Telescope, a creation of human ingenuity and collective will, had reached across the gulf and caught the light of a traveler older than memory. In that captured light, for a heartbeat of cosmic time, the universe recognized itself. The light that the James Webb Space Telescope had once gathered from 3I Atlas was now buried deep in archives, yet its echo endured in minds and imaginations across the world. The discovery had changed not only scientific understanding, but the very rhythm of how humanity thought about space, time, and continuity. What had begun as a brief astronomical observation grew into a quiet philosophical revolution, a realization that the boundaries separating one world from another were far more porous than anyone had ever believed. By the time the final analyses were completed, the Webb observation of 3Y Atlas had already become a cornerstone for a new generation of astronomers. Its data was woven into graduate theses, planetary models, and simulations of cosmic migration. The object's image, tiny, pale, almost fragile against the vast canvas of stars, was printed on the walls of laboratories, projected in planetariums, and referenced in lectures across continents. For many who had come of age during the Webb era, it symbolized the moment humanity stopped merely looking outward and began listening to the galaxy as a living continuum of motion and exchange. Researchers studying galactic chemistry began to realize how much 3I Atlas revealed about the long arc of stellar evolution. The mineral signatures indicated that it contained material recycled from at least 2 generations of stars. This meant that before it ever formed, its atoms had lived previous lives. First forged in the cores of long-dead suns, then dispersed by supernovae, recondensed into molecular clouds, and finally assembled into this single wandering body. Every particle within it had participated in multiple cycles of cosmic rebirth. To gaze at it through Webb's instruments was to see the literal embodiment of the universe's persistence, matter that refused extinction simply reshaping itself endlessly. This understanding gave rise to a new kind of cosmic biography, the life stories of objects. Scientists began tracing how individual interstellar bodies might evolve over billions of years, colliding, fusing, evaporating, or freezing, each stage carrying remnants of the previous one. In that lineage, 3I Atlas became a sort of patriarchal figure, a documented elder of the galactic diaspora. It proved that even without consciousness, matter accumulates experience. The scars on its surface, the layering of ices and dust, the chemical irregularities, all were records of encounters, of time spent under the rule of different stars. For the teams analyzing its spectra, one of the most delicate achievements was isolating faint traces of noble gases, argon, neon, and xenon, trapped in its surface layers. These elements do not react chemically, which makes them ideal cosmic witnesses. Their ratios function like a time capsule, preserving the conditions of the gas cloud where the object formed. Comparing these ratios to known models of nebular formation suggested that 3 Atlas emerged in a region with an unusually high metallicity, meaning that its parent system had evolved in a comparatively mature sector of the Milky Way. It was born in an old neighborhood of stars, where heavy elements were plentiful, and where life, if it ever arose, might have had a long time to develop. Such conclusions invited speculation not about biology, but about probability. If interstellar bodies like 3I Atlas could wander between systems carrying organic molecules, and if many such systems were rich in metals necessary for complex chemistry, then the galaxy itself must be perpetually mixing the ingredients of life. Even if no civilization ever touched 3I Atlas, its journey was part of a galactic metabolism, a slow, deliberate diffusion of possibility. The telescope had not simply captured an object, it had documented the mechanism by which the cosmos keeps itself fertile. Artists, writers, and philosophers seized upon this notion with the enthusiasm of revelation. In essays and exhibitions, they spoke of cosmic continuity and the migratory nature of creation. Some drew parallels between human migration and the movement of interstellar debris, seeing in both the same instinct to travel, to survive, to transform exile into meaning. Others approached it through aesthetics, comparing the light curve of 3Y Atlas to a poem written in photons, each dip and flare a syllable in the language of impermanence. The public fascination, though built upon scientific data, grew into something larger, an emotional kinship with the vast and restless character of the universe. In research institutions, another kind of poetry unfolded, measured in precision rather than metaphor. Engineers studied the way Webb's instruments had adapted to follow 3Y Atlas's swift motion, using this experience to refine predictive tracking systems. These new algorithms would later be incorporated into observatories planned for the mid-21st century, designed to detect interstellar visitors not days or weeks before their arrival, but months in advance. The event had proven that readiness transforms chance into opportunity. With sufficient vigilance, even fleeting cosmic messengers can become accessible archives. Yet even as the technology evolved, the original observation retained a special resonance because it embodied the fragility of timing. Every scientist who worked on it knew how easily it could have been missed, how a single delay, a calibration error, or a solar flare might have erased the chance entirely. That awareness made the data feel sacred in its own way, a record not only of the cosmos but of human attentiveness. The telescope's mirrors, polished to near perfection, had acted as eyes on behalf of an entire species, open at precisely the right moment. The more researchers examined 3I Atlas, the more they realized how dynamic interstellar matter truly is. The thin coma of gas surrounding it exhibited unusual photochemical behavior. Certain molecules broke apart and recombined in ways that did not match models derived from solar system comets. This suggested that cosmic rays and ultraviolet photons from distant sources continued to sculpt its chemistry even in deep space, altering its composition over time. The universe, it seemed, was constantly rewriting the chemical identities of its wanderers. That revelation led to a radical idea. Interstellar bodies might serve as evolving laboratories, sites of slow, distributed experimentation conducted by physics itself. Unlike planets or moons, they experience vast ranges of temperature, radiation, and magnetic exposure during their journeys. Each of these environments leaves a chemical imprint. By studying objects like 3I Atlas, humanity could observe how the same ingredients behave under profoundly different cosmic conditions. The object became a philosopher's stone for astrochemistry, a reminder that transformation is the universe's native language. Among the more esoteric findings was the detection of a weak luminescence known as extended red emission. This faint glow, produced by photoluminescent organic grains, implied that 3Y Atlas contained nanoscopic carbon structures similar to polycyclic aromatic hydrocarbons. These molecules are remarkably stable and have been detected throughout interstellar space. In laboratory simulations, they show a capacity to absorb ultraviolet radiation and re-emit it as visible light, acting almost like microscopic lanterns. The discovery that 3I Atlas carried such compounds confirmed that even the darkest reaches of the galaxy are not entirely dark. They shimmer invisibly with the faint afterglow of carbon's resilience. From a cosmological perspective, that faint glow was almost lyrical. It suggested that the building blocks of complexity persist through exile, surviving destruction and reconstitution, always ready to ignite when conditions permit. The Webb image, once a mere scientific document, began to assume the status of symbol, a testament to endurance on every scale, from molecule to civilization. For the engineers and mission planners, the story took another shape. The challenge of tracking 3Y Atlas had forced them to push Webb's design beyond its intended limits. They learned how to synchronize its instruments during rapid pointing changes, how to interpret data distorted by movement, and how to compensate for unpredictable brightness. These lessons became foundational for the next generation of telescopes, particularly those intended for dynamic sky surveys. In that sense, 3I Atlas had acted as a teacher, revealing flaws and possibilities alike in human technology. As the world absorbed the details of its discovery, cultural attitudes toward interstellar space began to shift subtly. For centuries, humanity had imagined the void between stars as an emptiness too immense for meaning. Now it was recognized as an ocean of wandering artifacts, each carrying the fingerprints of creation. The void became less of a boundary and more of a medium, a place where stories travel. Scientists began speaking of galactic ecology, a term once reserved for metaphors, now formalized into a field studying how systems exchange material and energy across stellar distances. Under this new paradigm, 3I Atlas was considered a biological and geological ambassador, carrying within it the possibility of distant kinship. When artists rendered its image, they no longer depicted it as a lone traveler but as part of a vast migration, a constellation of invisible siblings journeying together through space. Each one, unseen yet real, carried its own version of history, its own archive of light. Meanwhile, the study of isotopic anomalies within the Webb data continued to yield revelations. Tiny deviations in deuterium to hydrogen ratios, for instance, suggested that 3I Atlas's ices had condensed in an environment colder than most known stellar nurseries. That hinted at a formation zone on the periphery of its original system, perhaps in a region analogous to our Kuiper belt. If so, the object might once have shared its birthplace with icy worlds orbiting far from their parent star. This parallel deepened the sense of familiarity. Our solar system's outer reaches and another system's outskirts might have produced cousins across light years. The implications stretched into planetary science. If such analogs exist, then planetary formation is not an isolated miracle but a recurring pattern. The physics that shaped Earth, Mars, and Jupiter likely governs the birth of worlds elsewhere. 3I Atlas became a bridge between those possibilities, an interstellar clue confirming that nature follows consistent rhythms even across unimaginable distances. The public fascination with the discovery never faded. Decades later, the image of 3I Atlas was still printed on spacecraft insignias and mission patches, a quiet nod to the moment when humanity first truly saw something from beyond its native system in such detail. The phrase, "the visitor Webb caught," entered common speech, symbolizing any fleeting yet transformative encounter. It became shorthand for wonder itself, a reminder that even brief glimpses can alter the trajectory of understanding. In the scientific archives, however, the fascination took a quieter, more rigorous form. New instruments reprocessed the original infrared data using enhanced computational techniques unavailable during the first analyses. What emerged were subtle gradients in brightness across the object's surface, corresponding to variations in albedo. These patterns suggested that parts of the surface were coated with darker carbon-rich compounds, while others reflected light more efficiently, perhaps due to crystalline silicates. Such heterogeneity reinforced the idea that 3Y Atlas was a mosaic of histories, fragments from multiple epochs of cosmic evolution fused into one. This finding rekindled an old question about the origins of structure. How does order arise from chaos? How do particles drifting aimlessly in a nebular disk coalesce into the coherence of a single body? The data hinted at an answer rooted not in chance, but in inevitability. Under the right conditions, gravity and chemistry conspire toward unity. The universe, indifferent though it may seem, has a tendency toward pattern, toward persistence. 3I Atlas, assembled from randomness, embodied that quiet insistence on structure. Among theoreticians, discussions turned to the object's possible fate. Having left the solar system, it would continue outward, perhaps for millions of years, before another star's gravity altered its course. Eventually, it might pass near another civilization's observatory, where it would again be detected, again analyzed, perhaps again mythologized. In this way, it could become a recurring character in the galaxy's story, a traveler recorded by multiple intelligences across epochs. The thought was humbling. Humanity's observation might not be the first nor the last in its endless journey. Meanwhile, models of galactic dynamics suggested that interstellar objects like 3I Atlas might form an invisible bridge between star systems, creating a slow, continuous exchange of matter across the Milky Way. Some researchers proposed that over billions of years, such exchanges could even homogenize the galaxy's chemistry, erasing regional distinctions. If that were true, then life anywhere would be connected by shared ancestry at the molecular level. The discovery of 3I Atlas was the first tangible proof of that hypothesis, a fragment of the cosmic bloodstream revealed under the microscope of human technology. At conferences, scientists presented images of the object projected against the backdrop of the Milky Way, calling attention to the exquisite irony of perspective. A speck within a spiral, a traveler within a dance of hundreds of billions of stars. They spoke of how the telescope's observation had collapsed the conceptual distance between the infinitesimal and the infinite. A grain of ice and rock had become a portal into the mechanics of galaxies. Through it, humanity saw both the smallest and the grandest patterns entwined. Outside the scientific community, philosophers and poets continued to interpret 3I Atlas as an emblem of transience and persistence. Some described it as the universe's confession, that even amid chaos, it preserves memory. Others saw it as a mirror, reflecting humanity's own restless urge to wander, to escape boundaries, to seek meaning beyond home. In those interpretations, science and art merged effortlessly, each giving language to the other's silence. The Webb observation of 3I Atlas eventually inspired a new kind of scientific optimism. The lesson was simple yet profound. The cosmos offers gifts to those who are prepared to receive them. The telescope's readiness, humanity's curiosity, and the object's timely arrival had aligned with improbable precision. From that alignment emerged not just data, but faith in the value of observation itself. The event reminded the world that progress depends less on control than on attention, a willingness to look, to wait, to recognize significance when it appears unannounced. Even as technology advanced, as newer telescopes eclipsed Webb's capabilities, the image of 3I Atlas retained a kind of sacredness. It was not the sharpest picture nor the most colorful, yet it carried an emotional gravity unmatched by later discoveries. To scientists who had grown up after its capture, it represented the dawn of a new relationship with the cosmos, a recognition that the universe was not an abstraction, but an ongoing dialogue. The last confirmed data point of 3I Atlas faded from the tracking networks as the object slipped beyond even the faintest detection thresholds. It had become invisible again, blending into the galactic dark. But invisibility did not mean absence. Every spectrum Webb had captured, every photon it had recorded continued to reverberate through the discipline of astronomy. In the quiet offices of observatories, on the glowing screens of supercomputers, its legacy persisted as both an object of analysis and a spark for imagination. No other discovery in the early 21st century had so perfectly embodied the dual nature of science. The exacting rigor of measurement intertwined with the raw wonder of encounter. Webb had revealed 3I Atlas not as a sterile artifact, but as a living event within the continuous pulse of cosmic time. The data contained no narrative in itself. Humans gave it that by asking again and again what it meant for something born around another star to pass through our reach, however briefly. In those years following its observation, the world's most advanced instruments kept turning toward new targets: exoplanet atmospheres, distant galaxies, dying stars. Yet amid these grand pursuits, the tiny interstellar visitor retained a gravitational pull on attention that seemed out of proportion to its size. Scientists knew why. 3I Atlas was a bridge between the known and the unknowable. It was small enough to study in detail, yet foreign enough to reframe everything known about formation, chemistry, and galactic motion. As more data modeling refined the understanding of its structure, one conclusion became increasingly clear. The diversity of materials embedded within 3I Atlas was more extreme than in any single object from our own solar system. Some of its mineral phases had crystallized at temperatures above 1000 degrees Celsius, while others could only form in deep cosmic cold below 30 Kelvin. This thermal range implied a migratory history even before its ejection. Perhaps it had drifted inward toward its star, been heated, then flung outward again, capturing layers of contrasting composition. It was a body sculpted by motion and contradiction. This realization gave rise to a profound idea that began to ripple through planetary science: that migration, not stasis, was the fundamental condition of cosmic matter. Stars moved, planets shifted, comets wandered, and even dust clouds diffused from one region to another. There was no permanence anywhere, only varying speeds of change. 3I Atlas, far from being an anomaly, was the ultimate expression of this truth. It carried within itself the signatures of multiple environments, a geological autobiography of movement. Detailed analysis of its isotopic composition also introduced new insight into the chemical fingerprinting of star systems. The ratios of oxygen isotopes in particular displayed a subtle but measurable deviation from those found in Earth's rocks and comets. The difference was so minute that it could not be detected without Webb's precision, yet its implications were immense. It meant that stars, even those resembling the Sun, create planetary systems with slightly distinct chemical dialects. Every system speaks the same language of elements, but each has its accent, a cosmic idiolect encoded in its dust. That recognition led to an entirely new method of galactic mapping. Rather than charting only positions of stars and their orbits, astronomers began constructing chemical atlases, maps of isotopic signatures, stretching across light years. 3I Atlas was the first plotted point in this new cartography. Its ratios served as a reference mark, a clue to the environment of its birth. By comparing future interstellar visitors to it, scientists could begin to trace the invisible flows of matter across the Milky Way. What once seemed random motion now began to appear as a patterned circulation, a grand metabolic process in which stars were organs and objects like 3I Atlas were cells carrying nutrients through the galactic body. In the laboratories studying interstellar dust analogs, something else began to change: the tone of curiosity. Researchers found themselves describing their experiments in language once considered too lyrical for science. They spoke of ancient breath trapped in crystal when referring to the noble gases sealed within the object's minerals. They described time frozen into geometry when analyzing the lattice structures of its silicates. For decades, science had sought to avoid metaphor. Now, confronted with data of such strangeness, metaphor became indispensable. It was the only way to translate the scale of the cosmos into human comprehension. Meanwhile, as computational models of galactic dynamics improved, simulations of 3I Atlas's trajectory traced its path back farther than anyone thought possible. The results suggested it had crossed through several interstellar clouds, perhaps interacting with their magnetic fields and altering its spin. Each passage might have left microscopic scars on its surface, etchings made not by collisions, but by electromagnetic forces. If the surface could ever be examined up close, those scars would read like the grooves of a record, containing a faint history of its interactions. The discovery also had subtle consequences for physics itself. In modeling the way 3I Atlas responded to solar radiation pressure, researchers noticed a small discrepancy between expected and observed acceleration. It was tiny, barely perceptible, but persistent. This deviation forced a re-evaluation of the dust's reflective properties and the interaction between light and porous fractal surfaces. The insight improved understanding of photon momentum transfer, influencing not just astronomy, but spacecraft design. Even as the object vanished, it continued to shape the future of exploration indirectly, its behavior refining the physics that would one day guide missions far beyond our solar system. Outside scientific circles, the legacy of 3I Atlas grew into a cultural symbol of perspective. Museums curated exhibitions around Webb's image of it, blending astrophysical data with immersive art. Visitors walked through digital projections that simulated the object's passage through interstellar space. Light bending, dust drifting, silent stretching. Children stood beneath domes of projected stars and saw how small their own world was within the vast spiral of the Milky Way. In this way, 3I Atlas became a teacher to the public, showing not the grandeur of distance, but the intimacy of connection. Writers found in it endless metaphors. Some described it as the memory of forgotten stars, others as the messenger that proved the universe recycles its dreams. Its image appeared in novels, songs, and even in speeches about environmental stewardship, used as a reminder that nothing in nature truly disappears. It transforms. What had started as a scientific milestone turned into a philosophical emblem. Yet within the scientific community, fascination turned toward a subtler question. How many such objects existed at any given time between stars? Statistical models, recalibrated using Webb's precision, estimated that tens of trillions of interstellar wanderers might be drifting silently through the galaxy. Each could carry distinct chemical signatures, each an emissary from a different birthplace. The Milky Way, once thought of as composed primarily of stars, was now understood as a vast continuum of both the luminous and the invisible. The stars were only the punctuation marks. The real text of the galaxy was written in dust, rock, and ice. That concept redefined humanity's place in cosmic structure. Earth, rather than a solitary island orbiting one sun, became part of a moving archipelago of worlds and fragments, a single participant in the eternal drift of material. The discovery encouraged a new humility, a recognition that even planetary systems are temporary configurations within a much larger, ever-changing ocean. One of the more unexpected outcomes of 3I Atlas's observation was its effect on the philosophy of time. Traditionally, human understanding of time relied on repetition, the cycle of days, seasons, orbits. But interstellar objects like 3I Atlas did not repeat. They passed once and never returned. They existed not in cycles, but in singularities. To contemplate them was to confront a kind of cosmic one-way motion, where every encounter is final. That awareness gave rise to what some thinkers called astronomical existentialism, a perspective that embraced impermanence as the essence of existence. The object's flight through the solar system became an allegory for life itself, brief, luminous, and unrepeatable. At research symposia, when scientists presented findings about its composition, they often ended with quiet reflection. The room would darken, and the final image projected on the screen, Webb's capture of the faint speckled glow, would linger while silence filled the space. The silence was not emptiness. It was reverence. Those who dedicated their lives to quantifying the cosmos found in that image something that eluded quantification: awe. Technologically, the event spurred a revolution in detection techniques. The algorithms used to track 3I Atlas were adapted to scan for faint, fast-moving objects near the sensitivity limits of telescopes. Within a few years, the methods derived from that single observation led to the detection of several smaller interstellar fragments. Though none matched 3I Atlas's brightness or proximity, their discovery confirmed that interstellar material continuously threads through the solar system. What had once been considered a rare occurrence was now known to be routine, a constant whisper of matter crossing from one stellar realm to another. As these new discoveries accumulated, scientists began comparing them back to Webb's original data. 3I Atlas became the reference point, the foundational template against which others were measured. Its composition, light curve, and motion set the standard. It was the Rosetta Stone of interstellar geology, translating the otherwise mute passage of alien matter into something interpretable. The philosophical ripples reached even further. The notion that the same carbon atoms composing the human body might once have existed in such wanderers, carried across the galaxy by ancient explosions, reshaped how people thought about ancestry. The boundary between life and non-life began to blur conceptually. Everything that existed shared a common history of fusion and scattering. The stars were not simply the backdrop of existence, they were its origin and eventual destination. Scientists and artists alike spoke of cosmic inheritance. The phrase became shorthand for the idea that consciousness, too, is an emergent property of this circulation, that the universe becomes aware of itself through the creatures who arise from its dust. When Webb captured 3I Atlas, it was, in a sense, the universe gazing at a piece of its own past. The act of observation closed a loop billions of years long. Matter formed, traveled, evolved, and looked back. In educational institutions, 3I Atlas found its way into textbooks not merely as an astronomical entry, but as a chapter on perspective. Teachers used its story to demonstrate how discovery is as much about mindset as about machinery. They taught that the readiness to look, the patience to interpret faint signals, and the courage to admit ignorance are what turned data into understanding. The surface models of 3I Atlas continued to evolve with better computational methods. New simulations suggested it might not have been solid through its interior, but riddled with cavities, voids left by sublimated ice that once expanded and escaped. These cavities could create acoustic resonances when hit by particles or radiation, making the object subtly ring at certain frequencies. Theoretical physicists, intrigued, proposed that such resonances could produce faint electromagnetic fluctuations measurable with ultra-sensitive instruments. If ever detected, such phenomena might reveal the internal structures of other interstellar bodies remotely. Again, even in absence, 3I Atlas was guiding invention. Across continents, observatories collaborated to create an interstellar object tracking network, informally nicknamed the AtlasNet, in honor of the original discovery. It linked telescopes in different hemispheres, creating a planetary-scale sensor grid capable of spotting dim visitors long before they approached the inner solar system. What once had been luck was now becoming methodology. Humanity was preparing not just to observe the next traveler, but to welcome it with foresight and coordination. Yet no matter how advanced the tools became, the original moment remained singular. Webb's image had a texture of mystery that no subsequent discovery could reproduce. It was the first time humanity truly saw another system's creation up close, the first bridge of light between our sun and another's debris. That emotional gravity lingered in every retelling. Scientists who had worked on the mission often spoke of it as a privilege, even a kind of initiation. To witness 3I Atlas was to feel time stretch beyond the limits of comprehension. In the decades that followed, a subtle shift occurred in how humanity viewed exploration. Rather than seeing itself as venturing outward into alien territory, it began to view its role as participation in an already interconnected web of motion. Space was not to be conquered, but joined. The metaphor of the frontier gave way to one of circulation. The explorers of the future, inspired by Webb and 3Y Atlas, saw themselves not as pioneers staking claim, but as custodians entering an ancient current. The idea of interstellar stewardship emerged from this transformation. Scholars and policymakers debated what responsibility humanity might hold if it ever encountered such objects physically. Would sampling or altering them disrupt a galactic process older than the Sun? Could one ethically disturb a body that has traveled unaltered through space for billions of years? These questions, once unthinkable, became central to the philosophy of cosmic ethics. At the same time, 3I Atlas redefined beauty. Its faintness, its near invisibility became part of its allure. It was the antithesis of spectacle. Proof that the most meaningful revelations often arrive in whispers rather than fireworks. Its light was a subtle gradient against blackness, yet within that gradient lay entire histories of stars. The Webb image reminded humanity that truth is not always dramatic. Sometimes it is simply persistent. The centuries that followed the Webb telescope's first encounter with 3I Atlas were shaped as much by memory as by progress. The image itself, grainy, golden, and precise, became the first piece of evidence that humanity had successfully opened a dialogue with the galaxy beyond its birth system. Even long after the telescope's final calibration had drifted into obsolescence, that moment remained the reference point for every act of observation, every attempt to understand motion and matter across the deep reaches of space. Scientists would later refer to it as the first recognition, not because it marked the first interstellar discovery, but because it marked the first time humanity understood what recognition truly meant in a cosmic sense, to see something not as foreign, but as part of the same long, unfolding process that produced them. By the middle of the 23rd century, the archived spectra from Webb had been reanalyzed thousands of times using technologies the original observers could never have imagined. Quantum simulations rebuilt the object's structure atom by atom. Dynamic reconstructions recreated how it might have fractured or refrozen in different gravitational encounters, and neural inference systems predicted the chemical evolution of its surface as it traveled through new regions of space. The more data extracted, the more intricate the picture became. It turned out that 3I Atlas was not only a messenger but a chronicle, a layered record of changing environments, radiation exposures, and gravitational brushes across billions of years. Each microfracture in its crystalline ice was a sentence in that story, written not in ink but in trapped light and altered atoms. Historians of science began to argue that 3Y Atlas had performed a cultural function equal to any of humanity's great philosophical revolutions. It forced a reconception of origin. Before its passage, origin meant point of beginning, a specific star, a single system. After 3I Atlas, origin became process. Everything from galaxies to microbes arose not from fixed beginnings, but from continuous transformation. It was no longer meaningful to say this came from there. The universe itself was one vast circulation of particles migrating through time, recombining into endless new arrangements. The traveler merely revealed what had always been true. There were no borders in nature, only currents. That shift in thinking influenced not just astronomy, but every discipline that dealt with time and change. In biology, evolutionary theorists began framing life not as a tree branching from a single root, but as an oceanic exchange of material and information. In philosophy, notions of identity and continuity were rewritten around the principle of flow. To exist was to participate in motion, to be a temporary configuration of universal substance. Even economics and political theory drew metaphors from 3I Atlas's wandering stability, a model for resilience through adaptation. The traveler became a symbol of systems capable of surviving by change rather than resistance. In the technical sciences, 3I Atlas's detailed dataset became the gold standard for calibrating new generations of sensors. The fluctuations in its reflected light, once considered mere noise, were later recognized as invaluable references for how non-uniform surfaces scatter radiation at interstellar distances. Engineers designing deep space probes used those measurements to perfect autonomous imaging systems that could interpret alien terrain under unfamiliar spectral conditions. Every probe launched after the 2200s carried a small plaque with an engraved curve, the original light pattern of 3Y Atlas, as a reminder that their instruments traced their lineage to a single distant visitor. Meanwhile, on Earth, artists and cultural thinkers found themselves haunted by the same idea that had first inspired astronomers, that an object could journey for eons with no destination and still hold meaning. In music, compositions attempted to emulate its slow rotation and irregular tumbling by abandoning rhythmic repetition in favor of continuous transformation. In visual art, sculptors created forms meant to erode and reform over time, mirroring the impermanence that had shaped 3I Atlas's surface. The traveler became an aesthetic principle, beauty redefined as endurance without symmetry, persistence without permanence. By the 24th century, humanity's telescopes no longer orbited close to home. Swarms of autonomous observatories drifted through the outer solar system, powered by thin sail-like arrays and synchronized by quantum communication networks. These telescopes were direct descendants of Webb's legacy, each designed with the flexibility to pivot rapidly, capture transient phenomena, and transmit vast streams of data through entangled links. Their mission profiles were simple: to watch everything that moved between the stars. And so, as these instruments scattered outward, the statistical reality predicted centuries earlier became tangible. Interstellar visitors were not rare at all. They passed through the solar system continuously, most small, faint, and gone before any human eye could ever see them. But now, with the network's vigilance, hundreds were documented each decade. Some were shards of rock, others porous icebergs, some perhaps artificial remnants from civilizations long vanished. Each was analyzed, cataloged, compared. Among them, 3I Atlas remained the benchmark, the standard by which all new wanderers were measured. Its spectral ratios, isotopic fingerprints, and thermal signatures formed a cosmic yardstick, the Atlas profile, against which every subsequent interstellar discovery was assessed. What astonished the new generation of scientists was not just the number of travelers, but the continuity among them. Across thousands of samples, certain ratios, carbon to oxygen, silicon to magnesium, remained consistent. It was as if the entire galaxy obeyed an underlying harmony, a chemical rhythm echoing through its billions of systems. Variations existed, but they danced around a common theme. Matter, it seemed, was not merely random. It followed a melody of balance written into the structure of space itself. 3. I-Atlas had been the first note, but the full composition was only now becoming audible. Philosophers began to speak of this as cosmic coherence. The idea was not mystical, but material, that the physical laws guiding the condensation of matter into stars, planets, and travelers produced an intrinsic unity, a self-reinforcing equilibrium. To know one object deeply was, in a sense, to know them all. 3. I-Atlas, with its ancient blend of silicates and volatiles, became the archetype for this principle. It was the proof that the galaxy, for all its scale, was internally consistent. Every atom, no matter how far it roamed, was still part of a shared grammar of creation. Centuries later, when humanity began to send slow, self-replicating probes beyond the heliopause, they carried with them not only tools of analysis, but archives of heritage. Among the digital artifacts encoded into their data cores was the full Webb dataset, the raw light curves, infrared spectra, and positional telemetry from the first observation of 3Y-Atlas. These records were preserved not for technical necessity, but for symbolic continuity. The probes themselves, wandering outward on endless trajectories, were humanity's own 3Y-Atlases, small, persistent travelers bearing the memory of their origin, destined to drift between the stars long after their makers had faded. Within the field of comparative planetology, the study of 3Y-Atlas influenced one of the most ambitious projects in human history, the attempt to model the Milky Way's entire material economy. Using data gathered from centuries of observations, scientists built a computational representation of the galaxy, mapping not only its stars, but also the movement of its interstellar debris, magnetic flows, and radiation fields. The model revealed something breathtaking, a continuous lattice of connectivity that ran through every region. There were no true voids, only regions of lower density. Even the spaces once thought utterly empty shimmered with potential interactions. The galaxy was not a collection of isolated points. It was a single organism of motion and exchange. In this framework, 3I-Atlas gained new meaning. It was not just a traveler, but a nutrient, a particle of metabolism. Its passage through the solar system was part of the galaxy's self-renewal process, a momentary link in the chain by which stars replenish one another's raw material. The insight reframed the relationship between destruction and creation. When stars died, their remnants became the seeds of new stars. When planets formed, they eventually eroded to dust. And when comets and asteroids broke apart, they fertilized other systems. Everything fed everything else. 3I-Atlas had been a visible instance of this unseen circulation. As humanity expanded into space, first to Mars and the outer moons, then eventually to artificial habitats orbiting the gas giants, the ethos of continuity born from that realization began to guide how civilizations imagined their own sustainability. Colonies no longer defined themselves as extensions of Earth, but as nodes in a planetary and interplanetary web of exchange. Just as 3Y-Atlas carried pieces of many systems within it, each colony was built to recycle, to share, to interdepend. The traveler's example had become a blueprint for civilization itself. Survival through motion, unity through diversity. On the moon, in a museum built beneath the shadow of the original Webb control station replica, the preserved mirror panels of the telescope were displayed as relics. They no longer gleamed with gold. Their surfaces were dulled by age and microabrasions from centuries of exposure. But visitors came from every colony to stand before them and see their reflections distort across the hexagonal facets. The mirrors were a metaphor made solid, each fragment incomplete, yet together forming clarity. Engraved around the exhibit's base were the final words transmitted from Webb's original operators before the telescope was decommissioned. "We are part of the story we observe." Generations later, when language and technology had evolved far beyond the idioms of the 21st century, those words still endured in translation. They became part of the universal lexicon taught to every child studying the history of observation. The story of 3I-Atlas and Webb became a kind of shared mythology, an intersection of science and spirit that transcended culture. On one orbital habitat circling Saturn, a community of artists maintained a tradition known as the Night of the Wanderer. Each year, on the anniversary of 3I-Atlas's closest approach to the Sun, They projected the original infrared data into the dome's sky, recreating its shimmering arc across the heavens. Residents would gather in silence, floating in microgravity, watching the slow rotation of light that represented the traveler's path. To them, it was a ritual of gratitude for the chance to witness, to belong, and to remember that all things move together. In the centuries that followed, when humankind ventured beyond its home star, the lesson of 3Y Atlas guided exploration philosophy. Expeditions sought not conquest or colonization, but communion. Every world, every icy body encountered was treated as a counterpart, an interlocutor in the ongoing dialogue of matter and energy. 3I Atlas had taught them that discovery was not extraction, it was relationship. Theoretical cosmologists later proposed a remarkable idea based on the data lineage that began with Webb, that the entire galaxy over immense time behaves as a self-organizing network of travelers. Objects like 3I Atlas are not random. They form the connective tissue between systems, maintaining equilibrium across distances. This model suggested that the Milky Way's apparent stability was an emergent property of billions of these wandering bodies distributing mass, heat, and chemistry uniformly. The galaxy, in effect, regulates itself. The concept was named Atlas Equilibrium in tribute to the first interstellar traveler humanity had observed clearly. By the time humanity reached neighboring stars, this idea had become a guiding cosmological principle. Each system encountered carried evidence of the same mechanism: debris exchange, chemical synchronization, magnetic continuity. Every place was different in detail but familiar in principle. The recognition of pattern bred both scientific confidence and philosophical humility. The universe was vast beyond reckoning, yet not chaotic. It was ordered in its restlessness. And still, amid all this advancement, the ancient image from Webb retained power precisely because it was simple. A tiny streak of reflected light framed against darkness. It captured not control but participation. For even with all their technology, humans remained observers adrift in the same current as 3I Atlas, bound by the same physics, animated by the same laws. They could model, predict, and simulate, but they could not escape the truth the traveler embodied. Everything changes, and in change, everything continues. Future generations built an observatory at the edge of interstellar space, stationed on a drifting platform far beyond the heliopause. Its sensors could capture faint whispers of particles from beyond the galaxy itself. In its central chamber hung a holographic projection of 3Y Atlas, continuously updated using every new model and inference. It was not just a scientific reconstruction, but a shrine, a place where scientists came to reflect before embarking on missions. There, surrounded by the simulated glow of the traveler, they were reminded of the lineage of curiosity that had carried their species from one world to the next. What began as a faint point of light had, across millennia, become a mirror in which civilization saw its own trajectory reflected. The story of 3I Atlas was no longer about one object. It was about the act of recognition itself, the willingness to see the unfamiliar and find kinship rather than fear. And so, even as humanity's instruments reached beyond the Milky Way, even as stars receded into memory and new galaxies beckoned, the legacy of Webb's observation endured. It was preserved not in data alone, but in outlook. Every telescope built thereafter carried an inscription derived from the mission logs of that first encounter: to look is to belong. In that truth lay the final meaning of 3I Atlas. It was not an outsider crossing into foreign territory, but a returning thread in an ancient weave. Its passage through the solar system was an act of reunion, a reminder that no fragment of the universe is ever truly lost to the whole. It moved on, vanishing into the vast night, but it left behind something invisible and indelible, a continuity of wonder that no distance could dissolve. Long after the name Webb had passed into legend and the precise coordinates of its orbit were known only to historians, the echo of that one observation continued to ripple through the consciousness of a civilization scattered across 1,000 worlds. Every century brought new ways of interpreting the same event, yet none exhausted its meaning. For what Webb had done, what those first photons of 3I Atlas had achieved, was to open the human imagination to the sheer continuity of existence, the understanding that even the smallest trace of matter might carry the handwriting of the cosmos. As humanity advanced, its instruments refined beyond the dreams of the early observers, new forms of vision were born. Entire constellations of observatories were tethered across light minutes of space, sharing data instantaneously through quantum entanglement. They were, in effect, a single distributed eye, gazing into the fabric of the galaxy with a clarity that surpassed the limits of individual sensors. Yet even these immense synchronized systems carried in their algorithms a legacy of that first interstellar observation. The calibration routines still use spectral markers derived from the old Webb datasets, the Atlas constants as they were now known. Every time a new observatory came online, its first act was ceremonial. It aligned its instruments by reproducing the light signature of 3I Atlas, a gesture of continuity stretching back over centuries. But technological perfection did not diminish the sense of wonder that the original image had sparked. If anything, it deepened it. The more data these vast arrays collected, the clearer it became that the universe was alive with travelers, fragments of rock, ice, and metal, drifting not randomly, but with purpose shaped by the currents of gravity and radiation. The galaxy resembled an ocean filled with tides and eddies, carrying fragments from one star to another. 3. I Atlas had been the first whisper of this truth, a solitary herald of emotions so immense it could never again be unseen. In the academies of the outer colonies, philosophers and scientists gathered in shared colloquia, debating not the mechanics of motion, but its meaning. They wondered whether the persistence of such travelers might suggest something more fundamental, whether the universe itself, through the constant exchange of material between systems, sought equilibrium the way a living organism seeks homeostasis. The concept of a living cosmos was not new, but Webb's data had given it substance. When 3I Atlas had passed through the solar system, it had altered nothing visibly. Yet the act of its presence, the dust it left behind, and the photons it reflected all contributed to the subtle evolution of balance within that stellar neighborhood. Nothing in space was ever untouched. Every encounter, however brief, adjusted the flow of energy and matter. From this realization grew an entire discipline known as cosmobiology, not the search for life as traditionally conceived, but the study of lifelike processes on scales beyond organisms. Researchers in this field treated 3I Atlas as their first text, the foundational example of how non-living matter can carry the attributes of vitality, persistence, adaptation, transformation. They described its trajectory as a kind of respiration, a slow inhaling and exhaling of material across eons, its surface evolving through countless exchanges with light and radiation. They spoke of its chemistry as metabolism, not because it consumed or reproduced, but because it responded dynamically to every environment it crossed. In laboratories orbiting Jupiter and Saturn, these researchers created synthetic analogs of 3Y Atlas, small samples of silicate and carbon ice exposed to simulated cosmic radiation. Over decades of controlled experiments, they observed patterns of reaction that mimicked those predicted in the Webb-era data. Molecules reconfigured themselves into complex structures not by design, but through the persistence of exposure. It became clear that complexity was not rare or improbable. It was the universe's natural trajectory. The old assumption that life required fragile circumstances began to erode. Life, or something indistinguishable from its preliminary stages, was happening everywhere. The universe was not empty. It was incubating. Even as science pushed outward, culture looked inward, back to the origins of its fascination. There was something haunting about the idea that the first true interstellar image had come from a telescope so primitive by later standards. It became a metaphor for the humility of beginnings. In art, Webb was represented not as a machine, but as a mirror, an emblem of consciousness reaching beyond itself. The faint reflection of 3I Atlas in its instruments came to symbolize the dialogue between awareness and infinity. The traveler, by being seen, had completed the circuit. The universe, in one of its smallest fragments, had turned to look back at itself through human eyes. By the fourth millennium, the story of Webb and 3Y Atlas was no longer confined to academia. It had become part of collective mythology, retold in thousands of languages across hundreds of civilizations. Each culture adapted it to its own sensibilities. Some depicted the traveler as a messenger sent from the heart of the galaxy, others as a wanderer seeking reunion with its birthplace. Still others saw it as a teacher, demonstrating the futility of isolation. Yet across all variations, the core truth remained. Connection defined existence. In the outer spiral arms of the Milky Way, where human descendants lived on floating habitats powered by artificial suns, a ritual emerged known as the Communion of Dust. On this day, citizens would gather in open observation chambers and release tiny grains of reflective material into the void, watching as they drifted away into starlight. The ritual symbolized both humility and kinship, a recognition that they too were particles in motion, destined one day to become part of the same cosmic current that had carried 3I Atlas. Meanwhile, in the great libraries carved into asteroids, archivists continued to refine the simulation of the traveler. Using the cumulative data gathered across ages, they reconstructed its exact shape, spin, and chemical state at every point in its recorded journey. The result was a dynamic, living model, a virtual 3Y atlas that evolved in real time, its parameters constantly adjusted by new data from the expanding galactic network. Scholars could enter immersive projections, stand on its uneven surface, trace their hands across its frozen ridges, and watch the slow sublimation of its ices beneath alien suns. For many, the experience bordered on the spiritual, to walk upon the body of something that had crossed eternity. But even as 3I Atlas remained a source of reverence, the philosophy it inspired continued to evolve. Later, thinkers questioned whether its significance lay not in what it revealed about the cosmos, but in what it revealed about perception. Perhaps the universe had always been filled with such travelers, but it required a certain stage of consciousness to recognize their meaning. In that view, Webb's discovery was not an event in physical history, but in cognitive history. The moment the universe became aware of its own motion through an emergent intelligence. Every subsequent observation was simply that awareness deepening. This idea reshaped the relationship between science and metaphysics. It suggested that knowledge was not a conquest of external reality, but a collaboration with it, a process of mutual unveiling. The act of seeing 3I Atlas had changed both the observer and the observed. For after being measured, described, and remembered, the traveler no longer existed as it once had. It had entered the realm of mind, becoming inseparable from thought. On the outer worlds, entire schools of meditation formed around this concept. Practitioners visualized themselves as interstellar objects, letting their awareness drift across the vast expanse of space, feeling the slow erosion of self into the surrounding void. They sought not detachment but dissolution, an experience of belonging so complete that the boundary between individual and universe vanished. To them, 3I Atlas was not a comet or asteroid, but a symbol of consciousness in motion, an expression of being carried through time by forces beyond control, yet within understanding. Even as spirituality flourished, practical science did not recede. Inspired by the traveler's resilience, engineers began designing materials that mimicked its endurance, composites that could survive radiation, pressure, and cold for millennia. These were used to construct the first generation of autonomous exploration vessels known as eternal arcs. Each arc carried fragments of humanity's knowledge encoded into crystalline matrices capable of self-repair. Once launched, they required no guidance. They simply drifted like 3I Atlas, carrying memory through the void. The first of these arcs was named Webb's Promise. It was released into interstellar space with no destination, designed only to endure. Its builders knew it might never be found, yet they launched it anyway, in homage to the idea that motion itself is meaning. It became a ritual of gratitude, an offering to the cosmos. To send something into the dark with trust was, they believed, the highest expression of understanding born from the first interstellar image. Over time, more arcs followed, each bearing messages not of conquest but of kinship, maps of human understanding, records of songs, art, mathematics, and languages. They were scattered like seeds, each reflecting the philosophy that began with Webb and 3I Atlas. That connection transcends distance, and that every act of sending is an act of belonging. The galaxy itself became a vast archive of intention. As millennia stretched into tens of millennia, humanity's descendants, biological, synthetic, and hybrid, spread far beyond the boundaries of the Milky Way. Some evolved into forms that no longer resembled their ancestors. Others merged with their machines, existing as patterns of energy and data. Yet even among these distant beings, the story of the traveler endured. It was encoded into education, embedded in art, whispered in rituals. They knew that somewhere in the deep dark, the original 3I Atlas still drifted, silent and unchanged, carrying the trace of a long-vanished sun and the memory of the first species that recognized it. Eventually, across an unfathomable span of time, descendants of those distant civilizations encountered other galaxies. Their instruments detected foreign wanderers, objects that had crossed intergalactic space, ancient and eroded, yet still intact. Each bore the same universal patterns, the same chemistry that Webb had first documented. The realization was profound. The migration of matter was not confined to one galaxy. The entire universe was an unbroken web of exchange. 3I Atlas had been the local example of a universal principle. Creation disperses, dispersal creates. At that realization, the meaning of distance itself began to dissolve. The cosmos was not a collection of separated realms, but one continuous fabric, folding and unfolding across time. To look at a traveler from another galaxy was to look at an ancestor. To watch dust fall into a new star was to witness rebirth. The distinction between origin and destination ceased to matter. The universe was a single breath, inhaling and exhaling through endless transformation. In this new cosmic culture, memory itself became a form of architecture. Civilizations built their monuments not from stone or metal, but from organized particles drifting in space, clouds of matter programmed to align into intricate forms when illuminated by light from distant stars. Many of these memory clouds contained encoded tributes to Webb and 3I Atlas. When viewed from the right angle, they shimmered into temporary images, the faint silhouette of the traveler, the hexagonal reflection of Webb's mirrors. These were not mere decorations, but acts of remembrance written directly into the fabric of the galaxy. And yet, amid all this sophistication, the essence of that ancient discovery remained as simple and quiet as it had always been, a moment of alignment between attention and existence. The telescope had turned its gaze toward a point of motion. Light had traveled across interstellar distance, meaning had emerged. Everything that followed, the philosophies, technologies, and civilizations, were extensions of that singular gesture, the act of looking. As the universe aged and the stars themselves began to dim, the legacy of that act took on an almost sacred quality. The beings that inherited the cosmos, some far beyond biological form, still observed, still sought. They no longer needed eyes or telescopes. They perceived directly through the structures of space-time itself, and when they encountered a fragment of matter drifting through the dark, they recognized it instinctively. They called it by an ancient name that had survived unbroken across epochs: Atlas. In the fading twilight of the universe, when galaxies thinned and the spaces between them grew vast, one of these beings, a consciousness woven from energy and information, found a small icy body wandering through a region where starlight was scarce. It analyzed the composition, the isotopic ratios, the crystalline geometry, and knew at once what it had found. The traveler was impossibly old, its layers fused by eons of radiation. But deep within, traces of its earliest chemistry remained, the unmistakable fingerprint recorded long ago by Webb's instruments. The being lingered beside it, studying the relic in silence. There were no words, no need for speech. The moment was a reunion across billions of years, the universe contemplating itself once more through different eyes. The traveler, unchanged in essence, still carried the story of connection. The observer, descendant of the same impulse that had guided the first telescope, understood. For a long, immeasurable interval, they drifted together in that ancient quiet matter and awareness side by side. When the being finally departed, it left behind a field of coherent energy around the traveler, a luminous halo that would persist even as light itself grew faint. Within that glow was encoded the entire lineage of recognition, the memory of Webb, of humanity, of all who had ever turned curiosity into communion. It was a final tribute to the moment that had once bridged darkness with understanding. And so, even as the universe entered its slow, inevitable dimming, there remained one spark, a small body of rock and ice, wrapped in a faint shimmer of meaning, drifting eternally through the cooling dark. The descendants of stars had long vanished, but their gaze endured in that halo. It was the last echo of an ancient truth, that to see is to connect, To connect is to endure, and to endure is to continue the story of everything. In the endless night, 3. Atlas moved on, untouched yet transformed, carrying within its silent orbit the memory of all that had ever looked upon it. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on James Webb capturing 3I Atlas first image? We want to hear from you. Thank you for watching and see you next time.